Locus team. I'm Cameron.
I'm Min. Um, okay. To start, we will first talk about, you can hear me okay, right? To start, we will talk about the problem that we're tackling in this capstone. Um, Basically, for a long time, oceanography researchers have been measuring the dissipation of mechanical energy under the ocean at small scales on the order of millimeters. And the idea is measuring this uh, the problem is measuring these required devices that are expensive, easy to break, and hard to maintain. So the goal of this capstone project is to develop a device that is robust and can measure dissipation of energy at a reasonable price. There are many applications of measuring turbulent dissipation, which basically is just the gradient of two-dimensional velocities. And some applications, there are many applications, but basically we are able to develop a device that can measure turbulent dissipation for a low cost. Then many could be deployed over the ocean and much more data could be collected, which then will greatly contribute to the some oceanography applications such as weather forecasting, land mapping, and many important agricultural uses. Throughout this capstone project, we've explored three different ways of measuring turbulence. The first one being using a laser Doppler sensor, the second one being using pressure sensors in a differential configuration, and the third one being using a piezoelectric sensor, which is a flex sensor.
And then here's a quick demo of the latter of those.
So here you can see the assembly of our pressure sensor setup. And
yeah, there's just 5 pressure probes.
Here's a quick video of our sensor in a water tank with a pump pointed at, so we can measure velocities at different angles. And here is a video of our piezoelectric sensor, also mounted in the same way. And we're varying the voltage of the pump to see the difference it makes on the voltage measured by the flex sensor, which from then we can extrapolate the velocity. So for our first method, the laser Doppler sensor, we started doing this in the fall and half of last quarter. The idea is inspired by a paper by Edward Zarin in the American Journal of Physics. And in this paper, he pointed out that you can use a dual beam laser Doppler sensor, commonly found in gaming mice, to measure the velocity of flow in a fluid. And as you can see, this is the Bad Cat's Rat 5, and particularly we are extracting the PON 2020 sensor from this mouse. And the idea is laser will be emitted from the sensor, reflect off of particles inside the fluid, then recombine within the cavity of the sensor. From then, we can extrapolate the velocity using the energy self-mixing. Some potential issues that we thought about before beginning the test, 3 important ones. The first one being that the focal point could shift due to the discrepancy between the index of refraction of the lens of the sensor and the fluid we're measuring the flow in. The second being the scattering in water and fluid, generally speaking, is unpredictable, and therefore the performance of our sensor may rely on the orientation of the sensor and the direction of the flow. And also, the third issue, which perhaps is the most important one, turbidity, which is a measurement of opacity. The more turbid a liquid is, the more particles there are, measured in grams over liters. And we were afraid that the water we are measuring, particularly ocean water, would not be turbid enough for a laser to bounce off of and recombine within its cavity. So in the fall, we first started testing the sensor, and on dry land directly over a planar surface, results were promising because we were able to extract the X and Y position versus time in this graph here. We achieved this using a driver written in Tcl and X input of Linux. So since the results of our first dry test was promising, we directly moved to our first wet run, where we have the sensor facing up and a pump pointed a pump position such that flow is directly above the sensor. And from this, we couldn't see any significant data that was discernible from noise. So we decided that we should add some more particles into the clear water. So we added potassium carbonate. And even when we ran out of potassium carbonate, we couldn't get any good results. So we move on to our next testing setup. And basically, the setup is we have a plate directly below a sensor that's pointed downwards and driven by a stepper motor. The idea is, since it's driven by a stepper motor, we can easily figure out the tangential velocity at the point the sensor is pointed at the plate. And we wanted to see for which distance between the sensor and the plate, for which velocity and which turbidity of the water that we could measure the velocity reliably. And from this, we concluded that the sensor is not very good for this use case in measuring turbulence because the distance required between the sensor and a planar surface is very small. And furthermore, the turbidity will be much higher for it to be practical than typical ocean water. So then we decided to move on to other sensors.
So moving on, the next method that we tried to use was differential pressure sensor. So as you can see on the picture on the right, it's sort of a probe that you put into the flow, and it has 5 holes on it, one facing directly forward, and then 4 at multiple different angles. And then I don't know, like in fluid dynamics, there's something called stagnation pressure. So when a flow comes up against a flat surface, it increases the pressure right on the boundary of that surface. So you can use that to extrapolate velocity. And then by using multiple different pressure sensors at different angles, you can sort of extrapolate the direction that the flow is coming from. So in that picture on the bottom, when the flow is coming at an angle, the pressure sensor on the left is reading a greater pressure than the pressure sensor on the right. And then using all 5, you can sort of extrapolate both the flow velocity and the flow angle. So in our use case, we would try and find the gradient of the flow velocity changing over time in order to get this turbulence measurement. This only works really in a 30-degree cone around the front of the pressure sensor, because for fluid dynamic reasons, if the flow is coming in at any steeper of an angle, you start to deal with all these interesting phenomena like flow separation, which can cause inconsistent pressure readings. Next. Oh wait, oops. So here's just a general layout design of it. I catted up a mounting head using 3D printing. The idea is that the lab that we're working with uses a commercially available sort of underwater system. They develop like submarines and motors for research and commercial purposes. And the idea is that this would like be interoperable with the lab's pre-existing underwater enclosures. So it was designed to fit their 4-inch design. So like here are just some CAD renderings. Here's a cross-sectional view. On the far right, there's an image of the pressure sensor we used, and then the steel bung that we epoxied inside of the part in order to create like a watertight seal. And then on the bottom is just a really simple block diagram. So we have 5 pressure sensors going into the multi-channel ADC of an STM. And then from that, we're writing just the raw data and timestamps to a SD card, and then we do further analysis in MATLAB. So here's just a quick slide showing the general assembly. So we have this 3D printed part, and it's mounted to the flange end of the Blue Robotics sensor. Here's just a general view of what the enclosure looks like. And then that's a view of like the assembled test setup. So then we started to do some testing runs with this. The general idea for the workflow required to get the sensor up and running is in order to use it in like an unknown environment, you have to first characterize the sensor. So what that means is putting it in a flow tank at a known angle and a known flow velocity, and then creating a large lookup table of data points. And then from that, once you put the sensor in an actual real world environment with an unknown flow, you can sort of extrapolate from that lookup table and get your actual velocity and direction measurements. So we started this work. We weren't actually able to get it into the real world environment, but we started to work on calibration. And it looked promising with a few asterisks involved. That graph on the right is just a really simple graph with very little data processing, but what it shows is the pressure from the left sensor and the pressure on the right sensor. against theta, which is the angle that we had the flow going into the sensor. So there is a pretty linear. Actually, my theory, the data shows that it's linear, but I think it's actually just a zoomed in sine wave, which would make a lot more sense for the math involved. But it does show that there is differentiable pressure, so you can actually get angle readings. But the caveat to this is that we were only able to get this functioning at pretty high flow speeds, above about 2 meters per second, when the real domain that we want to actually be measuring is in the 1 meter per second, which doesn't seem like a big difference, but the function of stagnation pressure is a function of velocity squared. So that actually ends up being a pretty significant difference. So in the future, we'd actually want to use more sensitive pressure sensors or differential sensors, which allow us to sort of decouple the pressure sensors from just like the DC component, which is like depth. So yeah.
All right, so this is our last method. And basically the idea is we're gonna try to mimic one of the velocimetry sensors that the host lab is currently using. What they're currently using is called a piezoelectric beam. Basically what this like probe is gonna do, you're gonna point it in the direction of the flow. And what happens is the flow is gonna cause some stress on this piezoelectric beam. And when that happens, it increases the resistance of the beam, and from that you can get a voltage signal from it. So you can relate. So now you have a signal that you can work with. And the idea is we're going to try to use a commercial flex sensor that's cheaper and just see how well it can do in a custom graph. So this is the experimental setup, and we need to vary the velocity that the sensor's in, and to do that we have a pump, and we just changed the voltage across the pump. The dependent variable is going to be the voltage from the flex sensor. And we place the flex sensor perpendicular to the pump. Ideally, what we would do is put it parallel so that it won't cause water vortices to wrap behind the sensor and cause fluctuations. But even with that, the data came out okay. We did mitigate some of the distortion by placing it in this circular tub, because the way the pump works is that you need the water to cycle through. If you put it in like a rectangular channel, the water is going to go through the sensor, hit the back of the channel, and then hit the sensor again. So if you put it in this like racetrack configuration, it can cycle through circular without hitting the sensor twice. And then of course we use the op amp towards the end to amplify the small signal. So this is one of the graphs we have. It's just a histogram of the detrended output voltage. Detrended just means we subtracted out the mean. And I plotted four pump voltages, 8 volt, 10 volt, 12 volt, and 14 volt. And you can see that for higher voltage pump voltages, that means you have higher water flow. So the water is moving quicker, and you would expect the data to be more spread out, which is what we see with the purple. But then, like say for lower voltages, pump voltages at like 8 volts, it's more centered around the mean, which is what you would expect. And then, well, firstly, you can think of our time signal as having two components, the DC component and the AC component. And these two graphs just show that. So the graph on the left shows the mean. As you expect, if you increase the pump voltage, the mean also increases. And if you increase the pump voltage for the AC component, you would also expect it to increase. The goal of our project was to show that we could measure different velocities. And with the flex sensor, we showed that for different pump voltages, that you'll see a distinction between it. And from the different flow rates, you can relate it to the different velocities. We'd like to thank Professor Nick from Coast Lab, Professor Yoga, and our TAs Alex, Brian, and Eric.
Yeah, any questions?
That one. So you're trying to get what did you say, 1 meter per second?
Yeah, just in that general domain of
The Y14, whatever the highest voltage one there that gave you the most sensitivity to that.
so the actually if you go back in our anyways, in our test setup, it was only at the highest pump flow settings and the pump like right up against the sensor, like to the point where it wouldn't be giving different pressures to the different holes. It was only in that point that we were actually able to get like a coherent line or a coherent difference in the pressure sensors based on angle versus just the general noise. Because you're going to have, I mean, the pressure sensors are only rated plus or minus a certain percent of their maximum operating range. And then also, there actually were noticeable differences in the pressure from the top sensor of the array and the bottom sensor of the array just due to depth. So that alone was causing some issues. So it was only at really high pump voltages and flow speeds. The way I actually got the measurement is there's an equation for stagnation pressure. It's like 1/2 density velocity squared or something like that. So from that, you actually are directly able to measure velocity, but it only really worked in like the really high operating domains, which you wouldn't really see out in the environment that like on the sub or on and in any sort of like testing or data collection environment.
I see. So the Y, the lowest Y there, pump voltage was something you could measure, then you went up.
Yeah. So this graph really only shows the cherry picked like best case scenario, which is high pump speed, high velocity coming into the sensor. Any other thing, the line sort of was very noisy and squiggly because we wanted, like, I mean, if you do the math of what it's supposed to look like, zoomed out, this would look like a sine wave. So see centered at 0, 0, it's just passing the origin. So this looked promising, but in order to like actually do this in practical scenarios, we need more accurate sensors.
So what are the units?
The units, it's just in PSI, and then theta is in radians. So, yeah, no, it's not degrees. It's in radians. So yeah, it's just the zoomed in component of the pressure sensor. Or, yeah, it's just zoomed in on the sine wave that the pressure sensor would create.
So in all your experiments, one of your points of reference is this space. This will be floating on the ocean. So is that, how do you account for that? Don't you need like an additional sensor, like an accelerometer or some way to cancel?
So in the actual use case, the original like optimistic best case scenario is the coastal lab has a bunch of underwater ROVs or remote. Actually, I don't know what the acronym stands for, but it's basically remote control subs. So this was designed to be mounted on one of the data collection capsules on that sub. And the idea is for end case use is you'd have the sub going at a known velocity using the like accelerometers built into the sub. And then what you want to see is you want to see the flow or the flow speed coming in on the front. And then there would be slight variations going up and down of the flow velocity just due to turbulence that's naturally in the water, not the disturbance of the sub. And from that, you can sort of, I mean, you're placing these disturbances over time, but also distance because the sub's moving. And what that creates is sort of a vector field. And from that, you can get the gradient. And the gradient of that vector field is actually the end case turbulence scenario, right? So you're having a bunch of velocity vectors through space. And by taking the spatial gradient of that, you can get the turbulence and the energy dissipation, which is like the end case use scenario for this. Any other questions? They have a clicker. Is there an extra one? No, you don't need it. Just computer. I need a laser. Oh, you need a laser? Yeah. Is this a click? What is it? Is this a laser? Is there a laser on this? Do you have an actual? Check that one as a laser. Yeah, but they need to click. This is also a clicker. Just switch clickers. No, no, I'll just get it. Good. Is there a laser?
Which one did you guys?
There's like.
Welcome to our I-9 recognition PPT Capstone. And today we will be presenting our notice. We will be introducing the problems and going over our solutions to this problem. And towards the end, we will be presenting our work project, the issues that we have come across for working on project, and any potential future improvements. So beginning with the problem, one system of Americans will develop chronic cataract surgery by the age of 40, and more than half of Americans will develop chronic cataracts by the age of 80, which means that cataract surgery is very common. And because patients' eyes will usually rotate and move around during the surgery, this can make surgery very complicated and confusing. And this can be especially because surgeon's attention span will be primarily focused on the surgery. So our solution is Pinus, which is a camera system that utilizes machine learning in order to detect I-90 on the eye. It will be able to differentiate different anatomies of the eye periods, and it makes the system smarter and guides surgical devices to do eye-line administration. And it allows surgeons to focus more on the surgery. Now we'll introduce this.
I'm Megan. I'm Andrew.
I'm John.
I'm Ethan.
I'm Marco.
So this is our block diagram. On the front, you can see the FPGA. And on top of the FPGA, we have our camera that's mounted. And for the camera, there will be a live feed that is for whatever's in front of it. And it's displayed on the monitor with the mouse and the FPGA. The FPGA has no select buttons, but we didn't utilize it in our final product because this was primarily used for testing to see whether our model functions correctly. And the FPGA is also connected to a global receiver.
Okay, so a little bit about the workflow we have going on. First thing I do was obtain images for tagging and training the neural network. Images were sourced from Alcon surgery videos, as well as outside data sets, such as from IEEE and OpenEDS. From there, we tag those images. Afterwards, we take those images and we train our model, which we chose to be the tiny yellow V3 based on the darknet framework. The outcome of the training is a weights file. It's also important to note that we had to modify the configuration file for our use case, because the original darknet configuration was used to train on 80 classes versus our use case of only 3 classes. Afterwards, we ran our shell script to convert the darknet configuration, the weights, and the labels to the open source Onyx format. The output of that is our neural network and the .hex file. From there, we had to configure the post-processing C code and soft console to align with the neural network and the neural network's config. From there, clean, build, and generate the firmware. Afterwards, we have to load the neural network model to an available address slot in the firmware onto the FPGA and our software Libero. While we're still in Libero, we have to generate the bit stream and then program it and load it onto the FPGA. This is kind of a timely process, 15 to 20, since we only have one model. Next, power cycle the board and wait for firmware to be read from the SPI flash storage. After that, we have to test to make sure the system is functioning as we expect it to. Okay, so onto the component. Here's our FPGA. So this is the PolarFire FPGA, the MTF300 video kit made over by Microchip. It has 4 gigabytes of RAM, embedded programming debugging used by JTAG, 1 gigabyte of SPI flash memory, and USB to UART interface, which allows us to communicate with the board from our lab PC. It has HDMI 2.0 RX and TX, and HDMI 1.4 TX. So HDMI 2.0 TX RX are these guys, 1.4 TX is this guy. The main distinction between the two is if we want to use the live camera feed, we'd have to connect the external display to 1.4 TX, versus if we wanted to use the computer as our video source, we'd have to connect the computer to the HDMI 2.0 RX, and then connect the external display to TX. However, in our firmware and in our video kit, as of this version, the computer actually has to be connected to HDMI 2.0 RX, but the external display gets connected to HDMI 1.4 TX. So in that sense, it's kind of flipped.
Here's the camera that we're using with the FPGA, and that's onto the top of it. It is a Sony dual camera sensor over Amphenol FCI connector. It records in 60 FPS with 8.42 megapixel resolution. Here's the load select buttons that are on top of the FPGA, and it allows the user to pick and choose from a list of program models. At the top right, you can see us with a bunch of preliminary models and our tiny YOLO V3 model on the bottom. As we said before, this is mainly used for testing, and the first 4 models were demo models that we flashed onto the board to test and figure out the workflow of how to do that. And these are flashed and stored in spine memory. This is the microscope that we use, the True Vision 3D surgical camera. And it's not quite a microscope, but it works similar to one. Due to that, though, there was no fine coarse adjustment with this, which led to problems with the recording. But we utilize this mainly to simulate real life testing that surgeons would use our product for. And the FPGA camera attaches to the top of the camera so that we can monitor it.
For the following videos, viewer discretion is advised for close-up of eyes and sharp objects. So this is our initial model that we deployed in the recorder. It has 2 classes that it would recognize the iris and pupil. And one issue that we had with this model is that it was significantly overfitting to the surgical videos that we received, and that was mostly because we just had some training mostly on the images that we sourced from surgical videos. And so whenever you got like a normal eye, it had trouble recognizing the anatomy of it. One way that we mitigated this issue is that we increased our data diversity by sourcing from new databases such as IQ3 and OpenDBS. So this is our updated model that we deployed this quarter. It introduces a new class to recognize the instrument. And one significant thing to note is that the instrument class, or the instrument bounding gap, is sometimes can get pretty large relative to the size of the screen. And so sometimes it could cover up images of the anatomy of the people, for example. And so in order to mitigate this, we can just paint more images of instruments and also consider using key component training, but I will mention that later on in the future. This is the same model that is deployed on the microscope. As Peter mentioned, there was some reports of fine adjustment, so that we were not able to get a really good grasp of the zoomed in eye. This is a plastic eye, by the way. And we had to like kind of hold it up physically, so that one way that we can improve this model or structure is to build a structure, right?
Approach for the model is we found it's like a detection task. So we want the a convolutional neural net model, the YOLO V3 model. We had 3 classes we wanted to detect: the iris, pupil, and the instruments. Instruments were added later on. But due to the size of the FPGA's flash, we chose a tiny YOLO V3 for the purpose of the full model wouldn't fit on the flash, as well as like we wanted something small and efficient to run on the FPGA. The full model it will be able to run if at all, but it would be fast. The time model let us run the model at least like 30 FPS, which is enough for what we wanted to do. We used the darknet architecture, which allowed us to use libraries such as CUDA and OpenCV to accelerate our training process, and that allowed us just to train models fast on our own computers and deploy them onto the FPGA. So for our data sets, we had footage from Alcon, our sponsor. We used a script to split up the video into stills that we just annotated ourselves and then put into the training data. Additionally, we also sourced some data sets from IEEE and OpenEDS, which were just more data sets of eyes that we could add to our training to increase the diversity of our set. One thing we did run into was that after we trained our model, it had the weights file, we had to run a script to convert it to a file that was compatible with our FPGA.
but that kind of quantized our model a little bit, so that we did lose some accuracy. Though we did the best we could to train the model beforehand to mitigate that loss. The diagram we see here is a kind of a representation of our neural net model. It has beige and red boxes. The beige is for our convolutional layers, the red is our machine layers, and the purpose of like each is just for the convolution is for like feature extraction, the red is for like pooling, and that yeah, the pooling reduces our spatial dimension, just to make the feature extraction a little bit easier. And there's like two kind of paths you see at the very end. One just for like high level abstraction, abstract object detection. Other one just for like more fine grained stuff. It just allows us to do like multi-scale predictions, and that just helps the model along the way. So as for at least this quarter, stuff we completed was like we finished tagging the rest of our images, added a new category for instruments. We found new data sets, which were the attribute and the open EDS data sets, which were without cataracts, so we could have more diversity. And we finished training a new model and uploaded to the FPGA. So yeah, reduction of bias. Again, these are some new images. So active faults, this is kind of our like first deployment of our model. You can see that at least it can recognize something, but it's just a little bit inaccurate. This is our like the first iteration. When should we have this model working up? Which we have like the distinction between the iris and the pupil. You see on the first image on the left is like it has the, on the outside and the inside. The one on the right is kind of like where model kind of faltered a little bit when like the distinction between the iris and the pupil weren't really super clear. It's all one color there, but it still was able to recognize that something was at least there. And most recently, this is what we have now. You can see that the left side we have these still have the distinction between the iris and the pupil, as well as the instrument. And on the right side, we can see that even though there's two instruments, it gets to recognize both of them. But as Kenya was saying earlier, some of the instruments would be overlying over the eye itself, so it kind of had a little bit of issue when detecting the rest of the classes, but that would be some more work in the future improvements.
Okay, so we did run into some issues. First main issue was a bunch of out-of-date firmware. So the computer we received had two conflicting versions of pre-existing firmware. This led to the FPGA being unable to flash or even display anything. Second issue we ran into was a bunch of hard-coded post-processing C code with a lack of documentation. So a lot of the code was hard-coded and was not mentioned in the guide. This led to many issues that could have been resolved had there been proper documentation, such as random bounding boxes or the models not even displaying. The next issue we ran into is bad video drivers. So there's a problem with the HDMI output from our main lab PC and some of our own personal laptops that didn't allow for us to receive the video output from the board. This issue was seemingly random and out of our control and cannot be reproduced 100% of the time.
Although our model is pretty successful in recognizing that image related to machine learning, it's never perfect. So one way that we can improve the model is to first improve the images that we have. Because sometimes the model does not cannot differentiate between the visual and when they're between the color and size. So we can increase the data diversity. And also another way is instead of using a YOLO model, which is a bounding box model, we can introduce a feature-based learning that would detect, for example, the simple egg, and train using that instead, and that would mitigate the issue of the instrument covering the answer. Another improvement is to have a stable setup for the model to be mounted onto the microscope, because as I mentioned earlier, we were just holding it up physically, and it messed with like, the camera orientation. And so we can build a 3D printed case and also corresponding adapters that it would have a consistent camera feed. And finally, the scalability. Currently, our model in terms of size is significantly less relative to physical cameras used in real life. So it is not much of an issue, but we can also just minimize the fixed costs, such as the component prices and also the sophistication adapters. We would like to acknowledge Dr. Yoga, who is our Capstone lead, Alex Black, who is our TA, UK and Key, who are from Alcon, and Darrow, who helped us with technical from my. Thank you.
Thing I'm missing is suppose that you do perfect detection. But then what? If the eye moves and then I'm the surgeon, I have my tool in there, and so what follows from the eye moving and detecting that the eye moves?
So the point of the project is that because cataract surgeons look at the camera most of the time, they do not really look at their hands. But sometimes the orientation and rotation of the eye can get confusing when you just stare at the camera, and because it moves around a lot. And so by detecting the anatomy consistently, you're able to track exactly where your hand should be relative to the camera position.
So you would have some sort of guide overlaid over the image where you say you want to be here, but you're there, or have some sort of a.
Exactly. So you'll be running in real time while you're doing the surgery, and then so it will just consistently track it, no matter where, like your hand.
A dumb question. Was that just the confidence level? That was the number next to each box. So if I was a surgeon and I was like, I think that's the tool, but it says, 0.32, so maybe it's not. That's all that number was?
Yeah, essentially, it's just from the model itself that's processed onto the image.
Can you describe how the partition is done between what's done in is some identification, the recognition of the objects, is that done in FPGA gates, or is it all done in software, or is it a mixture?
So the model, so our neural network is trained on our data set and our images. However, the FPGA just has a bunch of accelerated hardware that has oh shoot, what is that? As a neural network accelerator that it runs on. So whatever it's trained on, its weights, its configuration and whatnot, is just going to be stored onto the FPGA and used as like the PC for the surgery.
And then like the software accesses that through a set of registers or something.
The software is loaded onto the flash drive, so yes. Laser pen. Okay. Ready? Stop working. Oh, let's do it. You do the transitions. Okay. Yeah. Hello, everyone. We're Team United Sensors, and this is our final presentation.
Okay. So drones are aircraft that can be operated without onboard human input. The versatility enables us to explore territories, respond to disaster, mobilize surveillance, and deliver goods. Most drones operate with each of their functions delegated to a single sensor. And while this approach is useful for saving construction time and price, single sensor systems give way to several problems. While in flight, wear and tear will eventually cause these sensors to degrade. When part of the system is compromised, the rest follows suit, leading to total system failure, at which point the unit will have to be repaired. Maintenance is expensive and it does not guarantee the issue from arising then. A solution? Sensor redundancy, operation that addresses the risk of sensor failure. By pulling data from multiple sensors, we can filter out errors and increase the precision of our operation. This increases the tolerance of our system, since the unit can pull data from unique avenues when functions are obstructed. This will give it a built-in backup system, since even if one of its sensors is out of commission, it'll always have backup that helps the unit stay on track.
So once again, our project is training sensor redundancy and quadcopter drone. So we'll first go about this by signing a new microcontroller that has the ability to have more sensors on them by having more communication lines, and design a new firmware and power definition file that we can build our from. Next, we'll define sensor redundancy by writing new drivers for sensors, including the IMU, barometer, and magnetometer, and uploading an open source code base for everyone to use. And then we also create a benchtop hardware testing unit, so we're able to test our firmware, hardware, and our software without having to physically launch the drone, which takes a lot of time. And then finally, we can design and print a custom PCB that will eventually mount onto the quadcopter and test it in real life.
All right, so this is our team. I'm Edison, I'm the team captain, also doing the firmware and sensor integration.
My name is Ethan, I'm responsible for all the software development.
My name is Tim, I did the PCB design.
Hey, my name is Hector, I work on the rovers.
Yeah, my name is Shmi, but I'm doing the telemetry communication.
So here's our block diagram. There's three main sensors that we're performing redundancy on: the compass, which is our magnetometer, barometer, and our IMU, and here are the data lines that is using to communicate with our microcontroller. For these three components, it'll be on our PCB, and like offboard will be these three components at the bottom: the rangefinder, GPS, and optical flow, all communicating via UART. And to communicate with ground station, we'll be using a telemetry radio. Ground station is where we aggregate all of our data. We'll be using Vision Finder. And the RC receiver and transmitter will be used to control the motors.
All right, so next we'll be going over the components. So first we have the IMU, which is one of the most crucial components. It, along with the barometer, are the two components needed for our RGPLA to even initiate. So this one is a 6-axis IMU that contains both the accelerometer and gyroscope, and we decided to use a custom printed board because the one for sale was a bit small, so we couldn't wire it very well. Also, this allowed us to default the board to SPI without needing to wire it.
So we use the magnetometer LAS3MDL-TR component, and this component is a 3-axis sensor which helps to measure magnetic fields, and in drones it helps to provide precise heading information and maintaining flight direction. And we're also using the barometer, which helps to measure the atmospheric pressure, and in drones it helps to determine the altitude by detecting changes in the air pressure, which helps for executing takeoffs and landings and maintaining stable flight levels.
So that brings us to the first of our modifications. Starting off with the compass. Our project is not able to support multiple instances of magnetometer, so I had to add that functionality. And I noticed that when you're on the drone or trying to initialize the flight, that it doesn't usually recognize multiple instances. So I had to have a song line recheck and take up the airlines during the initialization to make sure that they're all correctly. And as well as that, both barometers worked poorly, but for some reason, their calibration when put together was really correct. So I'm trying to take a more precise barometer that we had, but really great. So I changed the configurations to make sure that all the calibration is done before the flight actually starts. And this way, all the degrees is on each other.
So we are using the rangefinder TF minis, and what this component does is that it uses light in the form of a pulsed laser to help measure the distance between objects. And drones can use this for obstacle detection and avoidance when they're in flight during random landscapes and environments. And also we're using the optical flow sensor, the MATSEC 3901L0X, and this sensor detects motion by capturing images at a high flying speed and flying movement between all images to determine how fast the drone is moving.
For our mission, we have elected Neo6M as a GPS. This module features a ceramic antenna that helps the system be located from anywhere on Earth. When in action, this module returns latitude and longitude data, which is useful for tracking and enables return home functionality. The quadcopter is elevated with a set of 4 brushless motors. These light yet powerful devices can deliver a pound per thrust per unit. Within them is a set of magnets and coiled wire that spin in the presence of an electromagnetic field. Thanks to the lack of contact between the two, these motors possess greater longevity than its competition. The motors are calibrated with electronic speed controllers that act as the middle ground between the motor and the power supply. ESCs filter or function with PWM, which is time electrical signals. When the frequency of PWM is low, the drone will slow down. When it's fast, it'll speed back up. Or sorry, when the frequency is high, it will speed back up. This optimizes the power being sent to the motor by filtering wasted energy and increasing the energy or the lifespan of our battery. These sets of four are coordinated with an RX6R receiver that features PWM outputs and enables it to control 4 wings from a single point of entry. This module can be connected to an RC controller for wireless control or wired to a computer for telemetric ground control.
Right, so here's our PCB design. To your left is our layout, and to your right is a 3D rendering of the PCB. This is a 4-inch by 5-inch board. We decided to make it a bigger board to account for all our components and our vias. In the center here, that's our microcontroller, and then over here, that's the IMU. Over here is the compass, magnetometer, and then barometer. We also included an SD card to load it in the firmware, and it's communicating with the microcontroller via the SDMCC data lines.
All right, so while Tim was working on the PCB and Ethan was working on the software, I was mainly in charge of compiling all the sensors onto a board. For our test board, we decided to use a Nucleo version of the H743. On the left, you can see that's Hector's setup with the motors. Since the motors don't require RG pilot, he could do it separately from my sensors. On the right, there's a test iteration of our board with one of each sensor because we wanted to keep things clean to make sure they're all initialized on RG pilot first. It does get pretty messy, as you can see here. There's a lot of wires, it's 2 breadboards. It was too much, so we decided to move things onto a perf board. Here we soldered all the parts onto a perf board, and then we also 3D printed a housing to hold the board, the motors, and also have a window for optical flow and LiDAR to be able to see things. I also worked on the firmware. So the way firmware works in RG Pilot is first you declare a microcontroller. Thankfully, the H743 is already initialized on there. After that, I wrote a firmware file that basically declared all the drivers that we needed for the devices. And I declared the lines, the pins that are needed. And then as you can see on the right here, I've declared a bunch of SPI devices. I've declared 3 IMUs, 3 barometers, 3 compasses. And then finally, I compiled that and flashed it onto our board.
So moving on, we're going to talk about why we need DPF and really which is why it's needed. So I started this project, I at first thought that it would be easy to take the simple average of all the reliable sensors and get a very good evidence on top of that. But I soon realized that a slight faulty sensor can cause for a lot larger amounts of error later on, especially with gun flight. So I started to go with Archibald's idea of lane switching, which is essentially when you have an IMU and you have a going lane of sensors. So each IMU is assigned to a barometer, magnetometer, GPS, etc. And you're choosing the healthiest and most reliable way to have that. The reason they do this is because it's really difficult to kind of roll back and recalculate states when you're in gunfight. So just like having multiple lanes and switching between them, you have the best possible options. And the PKF does this by having the advantages from all sensors. So we aren't taking the measurements from all sensors in its live data and even the temporary future states. And here you can see the guys and magnetometer, for instance, you see the compasses in red because the threshold is set. It's obviously not helping out and increasing correct values. And so the ETF does it by first making the states based off map data and also the actions the drones have queued already. It takes measurements from all live sensors and then uses these and combines these for actual flight estimation. And then by repeating that throughout the flight, you have essentially healthy data and sort of over once it's standard. And then as well as this, my actual changes that I made to the PTM is that at first it was an IMU defined lane, and then if any of the sensors in the lane were unhealthy, it would just switch to an IMU and set the sensors. But I thought that this was really inefficient, especially with the amount of sensors that we had on our board. So I thought that maybe swapping out the magnetometers and barometers would be easier. So the only way to change lanes on IMU is faulty, but otherwise it will switch out instances of magnetometers and barometers where it's healthy. And to do this, I had to also just define what is a healthy barometer and ionometer. And so like you look at the IMU and see kind of faults they have there. And I thought that power loss, consistent non-changing values, there was simply huge large offsets that change the drone's position for all these values.
Right, next we'll be showing a software demo of basically the sensor failure. What you'll be seeing is a screen recording of the emission planner and also a video of us detaching the sensors. There's no audio. So yeah, basically, I'm initializing ArcherPilot by plugging it into the board, and it's currently starting up and detecting all the sensors. And in a bit, it'll go to the, I'll show the hardware ID showing all the sensors being initialized. And it takes a while because we have a lot of sensors loading up. So yeah, you can see that the IMU is being detected and that the, oh, let's do that. Yeah. So as you can see in the messages down there, the UPS is taking 3 IMUs. So it's initializing all 3 and then taking one of them. And you see there's a bunch of sensors being initialized down here. Now I'm unplugging one IMU and it takes a while to recover. But now it's recovered with 2 IMUs running. Then I unplug the next one. See here, it's detecting like a force reset. But now it's only taking 1 IMU. And yeah, that's our demo. So we'd like to thank Air Environment's Bill Tokumaru, Ryan Freeman, and Matthew Fell for helping us out and answering all our emails. We'd also like to thank Professor Yoga and Eric, our TA, for helping us out every week. Thank you. Any questions?
I think the algorithm for directly for detecting the sensor is faulty. It's a characterization for its sensor. You basically have a table of things that you are trying to measure, like voltage variability and stuff like that. And if you add new sensors into the redundancy program, you have to figure out how to check for their accuracy.
Yeah, thankfully, a lot of sensors, they have someone in the past, it's an open source code base, so someone past they take a shot at all these sensors and have those sensors kind of voltage faults and such. We didn't do that in our video here, so we can have a level way of demonstrating that failure, but that wasn't good.
The sound source. I know. I don't want to end the show though. Is there a way to? Should be coming on.
Yeah, yep. I think this one works. Or is he?
I think you should switch.
Yep. So they should take one. They should take one over there.
Yeah, we are.
And or the. Did you take any?
Yeah, they took 2.
One of them doesn't work. One of them
Yeah,
is
they
just
just need
for
a laser.
laser. Yeah. Okay, cool.
Am I doing that? They have their own.
You guys are gonna do it, right? I don't need to do it.
That's what we're doing first time.
Yeah, this is on. Yeah. So we are Team Pete, short for Procedure Execution Tracking Engine. I'm Anoushka.
I'm Sophie.
I'm Frank. And I'm Aaron.
So our team created an automated system called Pete to assist users as they perform a procedure. Pete has three main objectives: tracking the completion of steps, evaluating their accuracy, and identifying deviations from the procedure. So what are some potential applications of Pete? On the ISS, astronauts regularly perform space maintenance tasks and sometimes require support. Pete can help reduce their reliance on ground support by replacing it with computer assistance. Some other applications include in the medical field, where Pete could track the completion of steps in surgeries, or in schools, where Pete could help students when they practice for a technical exam. So we chose to train Pete to help users install the bottom bracket of a bike. We chose this procedure because it is meant to be analogous to a typical space maintenance task, in that it requires a variety of interactions between the user's hands, specialized tools, and machine parts. The procedure is also fairly complicated to complete without prior experience.
So now we've gone over the procedure. So first you install the spindle onto the frame. Next you install the bottom bracket and inside into the spindle and to the frame. Next you use a special tool called the double flat wrench that fixes the bottom bracket to the frame. Then you install the crank arm onto the spindle. Then to secure the crank arm, next, to put in the pedal. And then lastly, you set it in here with the pedal.
So as a single camera system, Pete benefits greatly from having an unobstructed field of vision of the user's workspace. So for the case of our procedure, we are using an overhead view of our setup. The way that the system is going to work is that as the user is performing each step in the procedure list that Spencer was just talking about, the system will validate the performance for correctness. So we've broken up the software flow into three main phases. The first is detection phase, followed by a validation phase, and then we display the result on a graphical user interface. So for the first phase, for the first detection phase, we are gathering and processing data from two different sources. So the first is computer vision and the second is sensors. So the purpose of using computer vision during the detection phase is that we want to get the bounding boxes of our objects of interest that's currently being detected in our live stream video feed as shown here. You're running a YOLO V7 tiny model on an edge device. An edge device is not going to be as powerful as a computer, which means that we can't use the full model because it's going to be very resource intensive. So as the tiny model has 6 million parameters, which is much fewer than the full version, it's going to be less resource intensive and it's going to be faster. And speed is important for us because our task is real-time object detection. And during the training process, we've also done a few enhancements such as image augmentation and transfer learning / fine-tuning. And the purpose of doing these enhancements is to improve our model's performance without necessarily having to collect much more data, which can be very time-consuming, as we've learned firsthand. So the second source is sensors. The purpose of using sensors is to identify rotation, temperature, and relative positions. We're using an MPU 6050 sensor, which comes with a gyroscope and accelerometer and a temperature sensor. We process these data to get things such as angular displacement, so we can use it to find rotation in the next validation phase.
And on to the validation process. This is basically how we check if each step is completed before moving on to the next step. So for the set structure, we have the main set as Spencer explained earlier, like installing the spindle, installing the double bracket. And here we have tightening the right frame with the double flat wrench. And each main step we have it divided into the subsets or criteria. Each criteria needs to be clear before it can proceed to the next main step. But first, let's talk about verifying the interaction between two objects. So the validation logic here is based on computer vision. We first check if an interested object exists in the frame. So let's say for the first step, we have installing the spindle. We will check if the spindle is already in the view. Then we can check for threshold. This means checking for the threshold for intersection over union. This is also called IOU. And this is basically looking at the right top video we have, which is overlapping between two bounding boxes. And for other supplements, we can use Euclidean distance and duration of frame for the bounding boxes. And second, we have verifying the tightening or rotation of motion using tools. So for example, we have a step which is tightening the pedal with the pedal wrench. So for that, we want to detect 3 rotations, and we separated this into 2 parts. For the first part, we have computer vision. First, as explained earlier, we first need to check if the bounding box are in the field. Let's say for this, we want to check if the pedal, if the pedal wrench, and the crank arm are all in the field. And if they exist, we'll check for continuous rotational coordinate change. This is only on the computer vision side. So that's why on the sensor side, we have a more accurate reading, which is from the sensor, and we will detect 3 rotation, which is angular displacement for 360 degrees rotation. But because of the noise coming from the sensor, so we have to use a filter to smooth out the signal. We use the exponential weighted average filter to do that. And lastly, we have also using the sensor to check for angular velocity so that we know that a rotation or tightening process is happening.
So the output from the validation phase is going to be something such as, yes, the step is being performed correctly. So we're just going to display that on our graphical user interface, and this is what our GUI looks like. So on the right side, we have a step list. This basically shows just whatever step the user is expected to perform as they go through the procedure. And on the lower right corner, we have 2 buttons. We have the revert and override. This is something that the user can click on in order to override the computer's decision, such as going back a step or going forward a step. And then on the left side, we have a video stream. This is whatever the camera on the board is seeing right now, and it's overlaid with our bounding box data from our computer vision model. And then third, we have the sub-step list. This is on the bottom center. These are the criteria that we were talking about during the validation phase. So the user has to satisfy all of these criteria before they can move on to the next step. Tool detection shows just whatever tool is being detected in the video stream right now. So for example, we are detecting the double flats wrench in this image here. And system stats shows the runtime and sensor connectivity status.
All right, so now that we know how our program structure overall works, let's go over the hardware block diagram and the software flow. All right, so this is our hardware block diagram, and I'm going to go over the specific components right now. So for our first portion, we have these 2 parts, which is our powerful SPC or single board computer. This is the NVIDIA Jetson or Nano. This is an edge device that's specifically designed to run AI or machine learning on a relatively small, relatively power efficient device. This thing has a built-in GPU, which is specifically designed to run all the tensor calculations required for computer vision. And then for the second portion, we have our Econ 81 camera. This is our high fidelity, wide angle camera that we use to monitor the overall workstation. It's very important to have both of these aspects in a camera for our engine here, because high fidelity is really necessary. Otherwise, you'll get a lot of noise, and that can really interfere with the object recognition model. As for the higher FOV or wide angle version, it's very important to have a camera that can record the entire workstation. Otherwise, you get hands, feet, or like maybe something else, or something that you want to record, or some tool or some part that's not being recorded when it really should be. And then, so this portion right here is our smart tools portion. This is our microcontroller, which is the ESP32S, which is responsible for interfacing with our sensors. It also uploads the sensor data to the powerful SBC, or Jetson or Nano, for sensor calculations and validation. And then as for our sensors, as Sophie mentioned earlier, we use the MPU 6050. It's a sensor suite that contains gyroscope, accelerometer, and temperature sensors. Although we currently don't use temperature sensors, this could be used in the future to detect if a tool such as a drill is overheated. And lastly, we just have a really simple external display, just a regular monitor that we use to display the GUI as well as the current progress of the procedure to the user. It also helps because it allows us to display the bounding boxes to the user for debugging purposes or just to let the user see what's really going on behind the scenes. Yeah, so this is our overall software flow. We'll start with the green portion right here. This is just our camera capture portion, which describes our how we get the raw sensor data from the camera to a usable video feed. We have the device driver, pre-processing, as well as the image buffer. All these are hardware accelerated, which run on board locally with NVIDIA's like state-of-the-art hardware, which allows us to run this stuff relatively quickly. And then this portion here is sensor capture, which is how we turn our raw sensor data, our gyroscope accelerometer sensor data, to a process sensor feed over IP in the NVIDIA Jetson Nano, which runs these two steps. The pink step here is the detection phase, which includes our object recognition model, as well as the sensor calculations for rotation, movements, location, yada. And lastly, we have our validation phase, where we separate all this stuff into substeps and basically determine if a substep is being complete by this computer vision and sensor calculation data. We can split these substeps into one of three separate categories. One is naive detection, as in is this part or tool even on screen? Two, IOU interaction that Aaron was talking about, or rotational interaction, which combines CV and sensor data to determine if a tool or part is rotating on the axis. As you can imagine, this is pretty important for the double flaps wrench or the pedal wrench that we use to rotate around parts. Oh yeah, and lastly, we have a user display input, which allows us to show the user what's really happening in the procedure, as well as allowing the user to override or reverse the procedure tracking system if necessary. It's always nice to have a little bit of redundancy.
So now that we introduce our system, here is our demo. On the left side, we have a top-down view of our setup. On the top left, we have a Jetson, and right next to it, we have our camera. This is our GUI. The GUI is currently being run on the Jetson. So first, we'll be introducing different random objects. So here we see tool connections. If an object is supposed to be there during this current step, it will be shown as red. Now we'll begin the first step. So this is our step list. Once a step has been complete, it will move on to the next bucket. Here we'll be demonstrating the undo and override button. So we set two effects. Here now on step 2, here we have the substep progress. So when every single step has been complete, it will be green. It all brings on to the next step. Here we have a double flash turn. So this tool has been modified to mount sensors and batteries. So the point of this step is to detect their realized sensor data and computer vision to detect the full location. So here we have 1 out of 3, 3 out of 3. Next, we'll be skipping from 4 to 7, because these 3 sets are kind of the same as the last 3. Here is also a rotation step. This one differs from double flash because of the sensor. the problem with this tool is that we try to mount sensors and batteries. The computer vision model had a really hard time recognizing the tool itself. So here, this is you can only use computer vision boxes, so you don't need computer vision.
Now, to like challenges for this project throughout the year. So on one hand, you have robustly identifying interaction from bounding box intersection and matching camera data with sensor data. For sensor, stable connection to Wi-Fi and reliable accurate reading was also difficult, but this was solved by using a filter. For another different part, the general performance, which is correctly identifying the object in a field and reduce false positives, and that was also difficult. And performance with obstruction, which is when a hand is over a tool or a foot is over another part of the bike. This is a difficulty in the computer vision part. And lastly, we have the board, which is includes stable connection to sensor, image processing, and general performance, and installing drivers and building libraries source also took a long time. Here's our team responsibilities for each person.
Thank you for listening, and thank you to our sponsors from NASA, Jessica and John, Professor Isika Polly, and our TAs, Alex, Eric, and Brian. Any questions?
The machine vision only rotation, the one that you showed at the end. Is it something that the model gives you, or are you just taking the coordinates of the bounding box and then?
Yeah, so that's a really good question. So for CV, like rotational data, so we experimented with different other models. So YOLO V7 sadly doesn't have a way to rotate the bounding boxes in a way that will actually show like real rotation. It'll just like resize the bounding box accordingly. YOLO V5 does have this feature, but it's less reliable, so we opted for YOLO V7. But so the current solution is, as you just mentioned, using coordinates, basically determining if a tool is intersecting with another part through the intersection over union calculation. And then we determine based on the bounding box which of the four like quadrants it's in. Like top left, top right, bottom right. And so to complete a full rotation, we basically say, okay, if it's intersecting enough with it and the coordinates are like X distance away and bottom left to bottom or bottom left to top left, that's like a 45-degree rotation. And then we just basically continue that for the whole way around to determine one full rotation. So that's the CV side. And then for the sensor side, we sample the angular acceleration and multiply that by the sampling rate to get an approximate idea of where the tool is or how fast the tool is moving. As you can imagine, if the sampling rate in our sense is a little bit on the lower side, so we have a lot of noise and stuff to deal with, as Aaron was talking about earlier. So that's why currently our solution uses 75% CV, maybe 25% sensors. Sensors are more there as redundancy. Hopefully in the future we'd be able to do it the other way around, where we use sensors more often than computer vision, since sensors tend to be a little more accurate this time for like most intents and purposes. For example, a sensor could determine if a tool is actually screwing another tool using a torque sensor. That was something that we juggled earlier into the project, but torque sensors are really expensive and mounting them on a tool presents other issues. So we'd like to, I guess this is something that we're planning to work on later in the future if we had more time. Any other questions?
Sorry.
This one was okay. One mic on the other side. Don't forget to turn it on. And then
This one? I didn't turn this one. Did I turn this one on? I don't know. This one also. I didn't turn. No, this one was.
You said you wanted to. Oh, you also have one. I'll do my. The first like 3 slide. Yeah. No, thing. Oh shit, you have speaker kits. Nice, I can do that. Oh, the professor. What? Where the hell did the professor go? Here we go. I have no idea. I have no idea. We just start or should we just start? I have no idea. Literally no idea.
Just start.
You just start?
I think just start.
All right. So we are Pengui, and this is our computer engineering capstone project. So what is Pengui? We are a team working with Pravium Research Inc., a Galibus company that researches and develops tunable lasers. Our task this year is to take one of their products, their laser developer kit, and redesign its user interface, replacing their current web-based approach with a local, not internet-connected interface. Some goals we had for this redesign were to make the developer kit as user-friendly, functional, and modifiable as possible, while also keeping it fully offline. And the actual product is a fully self-contained laser developer kit with everything you'd need to use a tunable laser and operate it, used by researchers and developers alike to experiment with a tunable laser for their research, their product, or whatever application. A few of the many applications of our product can be seen here, but for today, we have chosen to demonstrate 2 of them for you: gas spectroscopy and fiber optic shape sensing. And this is our development team. I'm Rylan.
I'm Rodney.
I'm Tori.
So here's an overview of the hardware and the development kit. Down here is the actual laser that they developed themselves in-house. And then the entire bottom half is all the supporting components that the laser needs to actually fire its output. Most of which are housed on connected directly to this driver board, which is also the existing project at Pravium Research. It contains temperature regulators, DAC, other things needed to set the actual parameters and keep them running in good working order. On the top half here, we can see the actual control side of things, which is composed mainly of 2 single board computers connected to each other over Ethernet. Our main focus has been on the software side and the hardware side of this top half, especially the reterminal, which we'll get to in a moment. Between the reterminal, which is the actual touchscreen interface, and the laser itself, is an important component, which is the tie-in. This is a single board computer with an FPGA as well. And it's used to actually, we're using it kind of as a server in our setup, and it sets the actual parameters of the laser and has an the FPGA is used for signal generation. It can also be used to collect data for various applications and we can get to later as well.
Other computer module is the C2 reterminal, which is essentially just a Raspberry Pi directly connected to a touchscreen monitor. We chose this because it's an off-the-shelf component that has Ethernet connection, which is the main connection that will be that communicates with the client. It also has optional USB ports if needed for other processes. And this is the SDL image of the overall dev kit. The dev kit itself is inside of this enclosure. And because we're adding this module in the region, this enclosure itself requires more modifications to accommodate for it. You see it's not actually currently designed for the region.
So here's the dev kit for like their PCB that they have, and essentially it has the laser, has an amplifier, has the pump that you use to power the laser, and we're just communicating with this UCSB as part of our project.
And for the software part of our Capstone project, we developed a Python-based GUI that allows the user to tune the data. So on the left, we have the main menu layout. We have two master control buttons, a voltage status button and a laser status button to turn the laser on and off. And on the left, we have all the tunable laser parameters laid out. We also have an idle screen that triggers after a period of inactivity or when you press the display mode button. Since the software runs on a C0 read terminal, we designed it to have a touchscreen friendly layout, so the buttons and text are spaced out evenly. We also made an intuitive counter that changes the parameters just by changing the digits on them. Also, the maximum and minimum values of the parameters are correctly interlinked so that nothing out of the ordinary happens. We also have a window for outputting sine waves. We have all the parameters tunable. We also have a waveform preview widget that removes the need for an oscilloscope. We also have an arbitrary waveform window that allows the user to load CSV files that contains arbitrary wave files with a tunable frequency. And this is used to periodically and dynamically change the amplitude and strength of the laser during tuning.
Here, this is a function that we added that wasn't part of the original GUI, which is temperature manipulation. So you can check the temperature of the amplifier, the pump, and the laser itself, just in case like a part is overheating or something's wrong. And you can set them to like the correct temperature in Celsius that you want it to be so that it's functioning. And it's controlled by a thermoelectric cooler, which is on the PCB. So here's a demo example of us just changing the parameters live. And so as the video plays, you can see me messing with the voltage. And this is static tuning, so only one wavelength is going to be really tuned into this. And so after I turn it on, I realized it's not tuned correctly, and so I changed the voltage again. And after this plays, you'll see this on the OSA, which actually lets us see the wavelength of light and the power. So the bottom x-axis is wavelength, the y-axis is the power in dB, and so you can see that it properly.
So, as I mentioned earlier, one application of our product is fiber optic shape sensing. Basically, it's a pretty intuitive name. The goal is to be able to visualize and display the shape of an object on a screen in real time as its shape is changing. So some equipment you will need to perform this is our laser developer kit, of course, some fiber optic cables, some strain sensors, a waveform digitizer, and a GPU. So to just give a brief high-level overview of how this works, you take an object, you wrap it with fiber optic cables. The fiber optic cables have the strain sensors embedded inside of them. You then blast the laser through the fiber optic cables, which are connected to the waveform digitizer at the other end. So you send the laser through the fiber optic cables, which sends a continuous signal to the waveform digitizer, which then pumps that signal to the GPU for various signal processing. And the key point here is with the fiber optic cables, with the flex sensors in them, as the shape of the object changes, as it twists, as it bends, as whatever happens to it, the signal sent from the fiber optic cables and strain sensors through the pipeline changes in a predictable way, and you can use this to extrapolate the shape of the object.
However, due to time and hardware constraints, we weren't able to fully finish the project. However, we were able to finish most of the data processing and achieve real-time FFT data processing and visualization. So here in a demo video, we have a waveform generator that simulates the output of the fiber optic cable And by tuning the frequency on the output, we can see a shift in the peaks of the data. As simple as it might seem, we are still taking 2 million data points every frame and doing operations on it. Note that it is per frame and not per second. And with the actual processing time on the GPU being 7 to 10 milliseconds, it enables us to render the data on the desktop interface at a decent frame rate around 50 to 60 frames per second.
So our next demo is the gas spectroscopy or Raman spectroscopy demo. And here we have a gas cell with hydrogen fluoride gas inside of it. And we're putting a laser. We split it a few times. So the laser goes through the gas cell and it also then it goes into a photodetector with a laser not through the gas cell. And so we are able to do a differential and see the absorption wavelengths of a gas to detect it. And also we have an NZI clock box, and that just so that we can find out which wavelengths we're seeing the absorptions at. So here's the entire setup in like a live video. So that middle block, the blue is the gas, the middle is the photodetector, and the right side is the MCI clock box. And essentially what we're doing is the laser does not tune linearly normally, so we had to create an arbitrary waveform, which was linearized based on the specific laser, so that we could get as close to a linear tuning time as possible. And so I'm just inputting the parameters here, and eventually you'll be able to see the absorption through the data collection that we do through the rectifier oscilloscope. So as you can see here, all those peaks are the wavelengths that are being absorbed by the hydrogen fluoride gas. Go to the next slide. Yeah, so here, those are the peaks on the right side, and on the left side is the reference block. And so what we use, so the X is the amount of samples, and the Y is the voltages. And so what we can use for the clock box is there's zero crossings. Like, I guess this image is not very like, it looks all lumped together, but there's zero crossings. And in the valid range, there's around 100 zero crossings. So whenever we see these peaks, we can find, we have our range of where, we have a range of nanometers, and then we can find what exact point we're seeing with these spikes. So if you go to the next slide, I did a derivative calculation based on the absorptions, and then on the bottom is the wavelengths I got, and they are within 1 nanometer of the real wavelengths that's cited by NIST, or like the people who determine the real wavelengths at the National Institute of Science and Technology.
Now, back to the hardware side of things, as you can see, this developed front plates of the dev kit enclosure. We've integrated the regional smoothly into the frame. Additionally, highlighted in the red is our breakout connector, which we've developed as part of the optional replacement of the red design. We'll get to.
Yeah, so as we mentioned just now, we can now replace the rectifier, essentially to save cost and complexity in the system. Basically, what we would do is we have one single board computer inside the lead terminal, which is actually our F-35 compute module, and it would talk directly to the laser, or rather, its GPIO would control the laser parameters directly, rather than a client server model. So this would remove the client server model and reduce the cost of the entire system by possibly a few $100s. The only drawback of removing the rectifier is we no longer have an FPGA, which is currently being used for signal generation, maybe some boutique options for the actual application as well. But to replace the signal generator, we had a DAC added, which is what most of the components on this PCB are doing. And that allows for low frequency or static signal generation, which is more than enough for a lot of applications. And that's all we have for you today. Special thanks to Mr. Yoga, TA,
the VCB that you showed in the setup, how far did you get in actually building?
Oh, yes, so it's currently, we've ordered it relatively recently and it's currently assembled, but not yet validated. So, unfortunately, we might not get a chance to.
Back on a block diagram where you were an FFT and a windowing and a.
Oh, this?
That.
Yeah.
Can you explain a little bit what's going on? What's the purpose of windowing?
Okay, so basically what happens is a continuous signal is being fed in, but most of it is going to be noise. So windowing is basically finding the correct portion of the signal that we want and then checking the deltas, like the shifts and peaks. We haven't really gotten to that step yet because we don't have the hardware actually set up. It takes a lot of fiber optic cables to have that actually done.
The reason that there's sheets is that each like date in the fiber optic cable kind of reflects like a different thing. So it's equal to
But like windowing in the lower left, that's in the length domain.
that's after FFT, right? So
That also includes, so it also includes getting the correct portion of the signal and then identifying the peaks correctly.
Peak in the length domain, I would think that would be a position on the cable. That's not right.
It should be in the wavelength domain because we look for, so fiber optic gratings, they will each fiber optic grating in the in the fiber optic cable will reflect a certain wavelength, and we will use that as like the golden standard. So like when the fiber optic cable is not strained or compressed in any way, it stays at a certain wavelength, and then we use that as a reference. Once we perform the FFT, we see a shift in the FFT peaks in the wavelength. And we could use the change in wavelength to determine what kind of change is being made to the fiber optic cable altogether.
oh, yes. You guys max out. Oh,
How do you define maxing out? I don't think it's optimal to max out a GPU ever, because if your GPU is getting maxed out, you're probably doing something wrong. So I guess that's a no. But we did do a lot of optimizations on the processing. Getting it to run under like 10 milliseconds is quite a challenge. Transition
Oh, so okay. One mic on the other side. Which one's the clicker?
So
yep. Oh, you haven't turned it on. I didn't turn it on. Actually, sorry. Which one's the clicker? These are all clickers. Do you guys get a clicker? Yeah. Kristen's one. This one. This one has a mic here. Check.
Check.
Cool.
Alrighty, good morning, everybody. Our group is Wilmer, and welcome to our 2024 Capstone presentation. The goal of our project is to create a facultative way for viewers around the Boston area to view transit information about the information around the Boston area. Kind of like project is an art piece that's supposed to be put in someone's home or office and shows them various information about Boston, Massachusetts Transport Authority and other relative information that would be important to commuters. So hey everybody, my name is Jake. Chris. And Zach. And Jack.
And my name is Sam. So next we're going to introduce our block diagram. So this is our block diagram. As you can see, we have one central microcontroller with a built-in Wi-Fi module and Bluetooth module. The Wi-Fi module is gathering data from the MBTA API, best time API, and built-in weather API, and our Bluetooth module is connected to our custom Android application via Bluetooth.
Our microcontroller also has two SPI channels, one of which talks to an LED display and the other which talks to the LEDs embedded on the board.
Okay, next we'll be talking about our components. So for our microcontroller, we chose the ESP32, which has a built-in Bluetooth and Wi-Fi module. For the LEDs embedded within the mount, we chose GL9823 individually addressable LEDs. And then for the LED display on the bottom of the mount, we chose these Max 7 which are facing today. All right, so here we have the PCB that's going to be located on the back of the board. At the top, you can see the ESP32 microprocessor, and like Jack just said, it has integrated Bluetooth and Wi-Fi, so that's why we have it isolated near the top so that the antenna doesn't get interfered with by any of the other signals on the board. On the right-hand side, we have the micro USB, and that's used to download all of our code onto that processor. Once we're done with that, we switch over to the DC power jack on the bottom, and that's going to be supplying 5 volts to the entire board via just a wall socket that we plug into. And an important part about that is that it's providing power to these current amplifiers here, and we need those to amplify the signals that are coming out of the processor because we're supplying power and signals to there are almost 200 LEDs, so that's why those are important. Next, we're going to talk about the physical map design and construction. So over on the left there, you can see the actual Massachusetts Bay Transport Authority rapid transit route. That's showing the subway map of the area. And then over on the right there, you can see our mocked up version of it, which was made of Legos. And then this thing is pretty large. It's 4 feet wide by 3 feet tall. And over on the left there, you can see that's our wiring path for the LEDs. These LEDs are wired up in series because they're individually addressable. And then over on the right there, you can see our initial in progress of the map construction. Over on the left there, you can see all the white spots there where it's going to be where LEDs are going to be placed. And then over on the right, you can see how we're actually mounting those LEDs. Next slide. So how we chose to construct this thing was start out with a base mounting plate that everything will be built off of. On the top side of that, we'll have the Lego base plate, which will be mounting all the Legos onto. And then you can see that through that, we're drilling all the way through that and then mounting our LEDs in there. And then on the back of that base mounting plate, we're going to be wiring up all of the wires to the LEDs. So over here on the right-hand side, you can see how we're wiring up those LEDs. So wired up in series, you have 1 positive and negative lines on the outside too, and then in the middle, we're wiring them up series, which will all be on the back side of that base line. So here's another diagram showing up how our LEDs are wired up in series. There's over, like Chris said, there's almost 200 of them, so quite a few connections that need to be made today. Next, we'll be talking about the Wi-Fi connection of data sources. So as we previously mentioned, we're using ESP32's integrated Wi-Fi module to connect to local access points. From that, we will be making HTTPS requests to different APIs, which we'll be talking about now. So for our first API, we're using the MBTA API. This is a public service provided by the Massachusetts Bay Transport Authority. It provides real-time information about public transit within the Boston network. From this, we're going to take positional information and directional information about all the trains and on the subway and rail system. And then we're also getting information about the next train arrival at user chosen stations. And then for our next API, we're using the best time API. This provides predictive information about the busyness level at any given train. We're using this to predict the deadline traffic at a station, at all the stations within the train and rail system. And then for our final API, we're just using the Open Weather Map API. This provides real-time weather information that we're going to use to get what the weather is like within the Boston area. And this will be displayed on the LED display on the bottom of that.
So next, we're going to be talking about the LEDs we're using to represent each train station. So the LEDs we're using, as Jack said before, are the PL9823 addressable RGB LEDs. Each one of these has 4 pins, one for data in, one for ground, one for voltage in, and one for data out. And as a result, like I said, they're wired in series. They're very similar to the WS2818 LEDs, which are those seen typically in dorm room lights, etc., RGB dorm room lights. And we're communicating to these LEDs using SPI. So in order to send data to these LEDs, each bit of data is represented by 3 bits in SPI. So if we want to turn the LED on, we would send the message 110. If we want to turn it off, we would send the message 100. Each color takes 1 byte of data because 255 is the total value of 255, leading to each color being represented by 3 bytes in SPI for each LED. So we have a few different map modes, one of which is our loading screens. So if the board is not connected to the Wi-Fi, it will pulse orange, and if it fails to connect, it will turn to red. If it does connect, and it's currently getting the Wi-Fi data, it will turn green, and then we'll begin to pulse green. Our main map mode is the train mode. Here we represent the status of the train using different colors. So the white light means there's a train at the station, green light means there's a train arriving at the station, and no light means there's no train arriving or currently at that station. We also have the busyness mode, which represents the pedestrian traffic around each station. So green means there's light traffic, yellow means there's light to medium traffic, orange means there's medium to heavy traffic, and red means severe traffic. We can switch to the busyness mode and the map mode using the Android application, which we will be discussing next.
Thanks, Sam. So the Android application is the next component of our project. It uses Bluetooth Low Energy on the 2.4 gigahertz frequency band in order to communicate with and control the board. And another aspect of the application that we had to come up with was figuring out our own custom JSON string protocol that allows us to deparse the incoming messages that we send the board and then control the board respectively. So we'll take a quick demo, a look at a demo of the application and how it would work. So here we're connected to the board. It's now connected, and we can send our Wi-Fi network information to allow the board to connect to the internet. We have username and password options if you're connecting to a university network for your net ID. At the top, we can toggle between the train and business modes, and we can also toggle between day and night modes of our LEDs. And we also have different options for our LED display. We can change it from the local time to the live Boston weather, as well as to the top 10 busiest train stations in the Boston area that'll give you information about train arrival information at those stations.
All right, so now we're going to go into the LED display. The LED display is made up of several MAX 7219 LED dot matrices. And so this display is going to be seen at the bottom of the map, and it's really just a chance for the user to get a more personalized experience with their map. For example, if the user lives near, for example, Harvard Station, they want to see what trains are going to be arriving there, what time they need to be there at Harvard Station to get on the train. They can go ahead and set it to the arrival and departure mode, and it will show them that information for Harvard Station. Or if they care how busy it is there, maybe they need to go to a different station if it's too busy at Harvard Station. They can track that busyness as well. Or also if they just want to see the weather and time around the Boston area.
Cool. Now we'll briefly touch on some of the challenges we face. We're pulling a lot of data and sending it out to LEDs and LED matrices. This requires a lot of different tasks, and one of the challenges with that is that we need to make sure that the schedules for all the tasks are done properly so that everything operates smoothly and efficiently. Another challenge that we faced was there's almost 200 LEDs on this board, and each of them requiring 4 connections. That additionally, having all the PCBs and everything else fired up, we had almost like 800 connections that need to be soldered, and then many lines in the back of our board. So just making sure that all the power is being delivered correctly, all the lines are fired up correctly, and everything is no signal is being pulled over the lines nearby. Another challenge that we faced was just designing this board the way that it would work. This board, like I said before, it's 4 feet wide by 3 feet tall, so it's pretty large and it's not decently heavy. So one challenge was making sure this board was light enough to be potentially hung on a wall, and also making sure it's visually appealing, because that was one of the rest of the project.
The next challenge we faced was the custom app design and development. So, like I said earlier, this app is still designed completely from scratch, from the ground up, and we had to actually implement, because we're using Bluetooth Low Energy, our own discovery and advertisement code which is a little bit different than what you might find on your phone settings if you were to use classic Bluetooth. And on top of that, we also had to derive our own custom protocol to communicate with the board, which was a little bit of a challenge as well.
One more challenge we faced was ensuring that all the software of our system wouldn't run into any problems with any API edge cases. Like Jack showed earlier, we're interfacing with 3 different APIs, and sometimes those APIs give us some difficult to parse data. So in the end, we figured it out. We don't run into any problems, but that was just another challenge.
And the final challenge we wanted to discuss was the incoming data management. So we're taking in the information from the MBTA API for all the trains at a system constantly. So we have to make sure that we're managing that data correctly and that we have enough space to store and parse that data.
Thanks, Sam. And now we'll take a look at our final product and how someone might use it on a day-to-day basis with our demo base. So here we go. The first step would be to turn the board on. And once we do this, it'll start trying to connect to the last used Wi-Fi network, which it has saved in its local file system. And just like that, the Wi-Fi network connection is successful as shown by the green pulsing LEDs. And on the right side of the screen, you can see our Android app now connecting to the board. Now our app is connected to the board. And just like that, we have our train data loaded in pretty quickly. And you can see by default, we have our local time displayed on the LED display at the bottom. We'll go ahead and change that to show the Boston weather information, and we can also toggle between day and night mode on the LEDs. If you can notice the subtle brightness of them there. Now on the bottom, we have the Boston weather information being displayed on the LED display. And we'll go ahead and change that one more time to reflect train arrival information at Harvard Station. And it's just a friendly reminder, white LEDs means that there is a train currently at the station, and green LEDs mean that there is a train arriving at that station. And on the bottom of the board, you can see we have 12 minutes until the arrival of the next train at Harvard Station. If you look closely at the board in a moment here, you should be able to see the LEDs updating all in real time. Then we just have an update. The next thing we can do is change the map into business mode. Again, business mode represents the pedestrian congestion levels at and around each station, and it's color coded. So by the severity of the foot traffic, so red is more severe and green is light foot traffic. We'll go ahead and toggle it back to the train mode and also change the LED display back to the local time. And just like that, pretty seamless and quick, we can toggle between our different train modes, and we're right back to where we started. And at the bottom of the board, you can see our LED display is now showing the local time. So this is how someone might employ and use our our Lego board on a day-to-day basis. We just want to acknowledge Dr. Ishipali, Dr. Young, and our TA Eric for all their encouragement and support throughout the year. Honestly, a lot of what we did here wouldn't have been possible without their help. So we thank them about it so much. And that's basically our presentation. Thank you guys. What questions you guys might have?
And this is our question. So the problem we're trying to solve here is that there's a lot of smart gloves out there that exist, but overall they're usually they're very expensive, they're overly specialized, or they're kind of nothing. However, we would like to have having an interface that interfaces the hand would be very useful and very intuitive for a lot of different applications. So as a solution, we decided to create a smart glove that would act as a universal. So for a couple of possible applications, the most obvious one that comes to mind is virtual reality. So being able to control a hand in virtual reality using your hand in real life would be, of course, very intuitive and it would be pretty cool. We could also use the glove to control autonomous systems and control a variety of systems. One example of which could be, for example, a grabber, which would be pretty intuitive. You could grab something in your hand by clenching the fist, and then the arm would grab it. And the third application that we came up with is maybe teaching sign language to people and correcting on their form while tracking their hand movements. So in order to accomplish these goals, we need a behavioral spec that looks like this. First, we want to be able to measure the rotational position of each finger within 1 degree of error. And then after that, we want to communicate all of this data at high frequency via Bluetooth.
Okay, so this is our block diagram. The microcontroller is a sensor connecting to the IMU CSI. On the left side, we have the sensor connected to the external AC, and to its right is the antenna, which is the Bluetooth module. And here are the specific stations of the controller. The microcontroller is placed on the back of the head. 5 IMUs are at finger tip, and another 5 IMUs are at the finger base. 1 IMU is separately placed in the center, and the microcontroller is on top. The next part is the PCB. In total, we design 3 PCB, including IoT, base, and the maple. I will introduce the maple first. So it's 4-layer PCB at the top. At the top is loosely arranged for adjacent connectors, which are used to connect the maple and the PCB. The second part here is the STM32 chip. And on the left side, we have the external AC, and with the button is the power conversion part, connecting to the USB port at the bottom. And the final part of the PCB is at the bottom right. This is the Bluetooth one. Okay, the next one is the IoT. There is an IoT chip at the top and a jack connector used to connect the IoT and the MU base at the bottom. The final one is MU base with an IoT sensor and UCSB connector, one at the top connecting to the IoT and another one at the bottom connecting to the baseboard. That's all for our PCB.
So next on is our component list. We have the BMI323 IMU, the spectral symbol flex sensor, the STM32 WB5FRG microcontroller board, the ADS1115 external ADC, and also the anti-static glove itself. For the microcontroller, we chose the WB5FRG because it has built-in Bluetooth low energy, and also 2 SPI ports, 2 I2C ports, 1 ADC ports, which will fulfill the connection needs for our sensors. For the IMU part, we chose the BMI323 because it has a 16-bit triaxial accelerometer, a 16-bit triaxial gyroscope, and it also consumes a really low current of 790 microamps. And since we have 11 of them on our glove, it's better to use an IMU that uses less power so that it has longer durability. For the flex sensors, the flex sensor we have has a flat resistance of about 7K ohms to 13K ohms. How it works is that when you bend it, it changes its resistance. And so we can simply build a voltage divider circuit and use the ADC to detect the voltage from the flex sensor and then convert them into the angles. From our testing, the accurate angles for this flex sensors is about 90 to 180 degrees, and that's why we place it on the palm part. For the ADC, we use the ADS1115 because it has 4 channels, and for the same reason, it has low current consumption of only 150 microamps.
Okay, so moving on to the software side of things, we've chosen to represent the entirety of the individual finger movement with 3 main motions, and I'll explain them here now. First, we have bend, which measures the angular bend of the first knuckle on your finger. It's kind of analogous to thinking of like typing on your keyboard. Curl is kind of the bend in your next 2 fingers. Think about the motion of like kind of making a C for curl. That's kind of the motion we're going for here. And then wag is the side-to-side motion of the finger, and this is the most intuitive. Just think of wagging your finger at someone. All right, so every finger has a bend, curl, and wag, including the thumb, but because the thumb kind of behaves differently than your other fingers, it has oppositional movement. We treat the bend kind of as a different bend called palm bend. And this is kind of measuring the flexion across the palm. Okay, so the internal representation of the finger is kind of all of this data stored on a structure inside the firmware on the glove called a hand structure.
This data is concatenated into two types of packets that we then send over two notification characteristics via Bluetooth. The first packet's a finger packet, and this is responsible for all the bend and curl of each finger, and that's all it is. And the second packet is responsible for everything else, so the wag of every finger, the flex sensor data, and also the back of the palm IMU. And this is all to a spec that we have written out. Kind of the idea behind this is anyone can create a Bluetooth application, and as long as they're receiving data according to our spec, they should be able to interface with our glove, no problem.
Yeah, so to dynamically update the internal modeling of the smart glove, so to dynamically update the internal modeling of the smart glove, we collect and process data from both the accelerometers and the gyroscopes within each IMU. And the reason for this is that each sensor has its own strengths and weaknesses. So the gyroscope provides us with instantaneous angular velocity in degrees per second. And therefore, to determine the rotational position, we are required to compute a discrete integral of the gyroscope measurements with respect to time. So this approach is robust to varying speeds of rotation and works in all three dimensions of rotation, so the roll, the pitch, and the yaw. However, it presents us with a unique challenge, which is that discrete integration, even with a low time delta, is prone to over or underestimation, and therefore results in our internal model drifting from the true angular position. On the other hand, the accelerometers provide us with three-dimensional acceleration, and at rest measures purely just gravity. This sensor reading is a lot more stable and is much more accurate than the gyroscope measurements, and provides us with a great gravitational-based positional reference with which we can converge our adrifted model. So while this is not true calibration, it has the effect of gradual and continuous a calibration-like effect. However, the drawback with the accelerometer is that it is unable to provide us with components of rotation orthonormal to gravity, and is less accurate during periods of high rapid motion. And so for us to achieve the high quality of precision for our smart glove, we wanted to fuse together the strengths of each sensor and at the same time minimize the weaknesses of each. So this led us to adopt a sensor fusion driven model that dynamically determines which sensor is more reliable at a given time based on two factors: the orientation of the smart glove and the speed of the motion. So to account for these factors, we needed certain metrics that would allow us to quantify the effect of each factor. So to quantify the speed of the motion, we use the magnitude of the acceleration vector, and to quantify the orientation, we use the pitch of the smart glove. So in general, the accelerometer data is weighed higher during periods of minimal motion and when the z-axis of the IMU is aligned with gravity, and the opposite is true for the gyroscopes. As the orientation of the smart glove changes, so that's pitched on its side, we weight the accelerometer much less, regardless of the speed of the motion, because now all the motion is orthonormal to gravity, so it's harder to pick up. And so this is what that would look like. It's just a short animation. So yeah, in this animation, the blue line is the accelerometer weighting, and the orange is the gyroscope weighting. And at the start of the animation, the glove would be pitched on its side, where the accelerometer is less reliable and gradually returns back to a neutral orientation. Yeah, and so we also have three tunable hyperparameters that, when modified, change the behavior of the internal modeling and the sensor fusion. The first one is the gravity magnitude offset, which sets the center magnitude over which the model would converge a drifted model. And at in these ranges, the accelerometer is also weighed higher than the gyroscope data. The second parameter is the peak constant, which changes the peakiness of the function, and in effect changes the range of magnitudes over which the accelerometer is weighed higher than the gyroscope. And at these ranges, it would also calibrate the model, a drifted model. And so this is another animation. This is what that looks like. And again, the blue line is the accelerometer weight, and the orange line is the gyroscope weighting. And as the peak constant changes, it stretches out the function. And the points at which the accelerometer is weighed higher than the gyroscope stretches out. And so it would calibrate at a larger for a larger range of magnitudes at rest. The last hyperparameter is the gyroscope bias, and this basically sets the minimum weightage of the gyroscope data and is especially useful when the gyroscope is providing us better data than the accelerometer. And this is what that looks like. Yeah, so again, the blue line is the accelerometer and the orange is the gyroscope. And whenever the gyroscope provides better data, we want to bias it so that we can rely on the gyroscope heavier than the accelerometer.
Okay. So we already talked about the relative finger data, the way we're measuring each finger. We have the bend, the curl, and the wag. And depending on which measurement we are taking, it changes which IMU we want to aim for. So you can see for the bend and the wag, we want to be using the palm IMU, the one in the center of on the back of the hand, and the base finger IMU as well. And for the curl, we want to use the base. So we take those and we just plug it basically into this software flow. In the top left, we can see the gyroscope change. As we said before, it measures an angular velocity. Each gyroscope does. We subtract those angular velocities from each other and then divide by the frequency to take a discrete integral, and that way we get our gyroscope angular velocity. From there, afterwards, we take the two accelerometer vectors that we get, take them as the gravity vectors. We take a dot product of them and then take an arc cosine. And from there, we get our accelerometer angular position. We plug these values into the sensor fusion algorithm that was just explained. We run it through a low pass filter, which is an exponential weighted moving average. And then we get our finger measurement. The thumb bend is a little bit different since it uses a flex sensor approach rather than using the IMUs. So we take our flex sensor data that comes from our voltage divider circuit. We run it through the onboard ADC, and then we recontextualize it. Basically, this means taking the angle of the flex sensor, subtracting it from 180 in order to get the bend of some rather than just the total angle of the flex sensor. And then from there, we have our thumb bend measurement.
Yeah, so we also developed a VR model of the smart glove, and this model was constructed using 3.js, which is a JavaScript-based graphics library, and is commonly used in VR modeling. And like the internal model, the model uses relative positioning for each of the fingers, and when connected to Bluetooth, it mirrors all the hand configurations you do in real life in the VR space. And so you'll see this later in the demo video.
To introduce ourselves, because we haven't done that yet, I'm Diego Hedis. I'm the team lead, and I'm also in charge of data parsing and hardware.
Hi, I'm Anant Palaka, and I'm the software development and visualization and application development.
I'm Jonathan. I was in charge of Bluetooth and communication for the smoke.
I'm Phil, and I'm in charge of hardware testing and PCB development.
I'm in charge of hardware testing and PCB development. And the next week is our demo video. We hope you will attend.
Yeah, just to cap it off, we'd like to thank Dr. Bali for all of his help and all of the other TAs as well, especially Eric, for meeting with us every single week. We'd also like to thank the International Foundation for Telemetry for providing funding for it.
But I got a quick question. On the slide where you were showing the to applying accelerometer versus the other, you probably said it, but I think I missed it. Why did the weight of the accelerometer fall off as the acceleration was higher?
So the reason for that is that we use the accelerometer measurement as basically a detection for where gravity is relative to the accelerometer. So when the hand moves around a lot, that acceleration vector kind of gets thrown up. So it's no longer representing gravity, so it's simple.
I get it. Thanks.
Sure.
So in the middle of the horizontal axis, for instance, one there, or is that 10?
That's 10.
So is 10 correspond to like when it's aligning with gravity?
So it's actually centered around 9.8, which is yeah, yeah. So it's, yeah, just a little bit off of 10, and that's just the magnitude of gravity at rest. Yeah, so
It's normalized, but it's
no, yeah,
not great.
it's a meter per second squared. Yeah.
So your spec was 1 degree off from the finger. How do you actually measure ground truth against your detection?
We don't actually measure so we didn't like take a protractor to our fingers per se, but what we did do was I don't know if you saw in the beginning of the wooden hand model, we were able to put the two IMUs on the tips of this wooden hand model, which is still, and move it back and forth and accurately determine whether, like at its still position, whether it was
But that's relative to that you're talking about the calibration of the bin. I think what like question is about being told when your sensors aren't when your model of where gravity is like so you said as you become hand around clock, you use the true direction of gravity. And at what point do you go, okay, I'm 1 degree off, I think that's 10 degrees off, and you reset?
So we use our centrifugation method. Basically, it says we have a curve, and that's kind of determined by what I'm just talking about, like P constant and all of that stuff. It's the gravity, the accelerometer readings progressively have less and less weight in a weight average, which our scope has progressively. Go ahead.
Is there any integrated feature in the glove for the absolute positional orientation of the hand as a whole? Or would that have to be handled as a separate thing for the
So that was a work in progress. We didn't quite finish that, but if we had more time, then we would have been able to finish that. We got it about like 50-60%.
Is the hardware there?
Yes.
Okay. Great.
Thanks. Any other questions?
If you don't use mic, it's going to go into recording. So you need to use mics.
Oh, we need to?
Yeah.
Okay. Yeah.
Or else it wouldn't go into recording. The pen is over here. You should take one over there. Or actually two. One person can just top this.
No, I think
There's
just
pass your mouth. Which one's forward?
yeah, just
Welcome, everybody. Welcome, everybody. First off, I just want to give a big thanks to everyone for being here. Appreciate all the work that everybody's put in. I really appreciate you guys being here, to acknowledge that everything we've done and everything everybody's done. It's been a great year working on this project. So welcome to Home Flow. So our goal here was to build a smart wearable device to, monitor the user's health. We ended up building a watch. We just thought that that would be the best form factor, as we want the user to wear it all throughout the day, but also, be small enough to not be cumbersome. And we built this product for everybody. Everybody can take advantage of its benefits just to, get a better understanding of their health. So to introduce us, I'm Ben Brennan.
I'm Brandon.
I'm Julian.
I'm Sayed.
I'm Marshall.
And we're Home Flow. So a little overview, what we'll be talking about is just, I already told you about our goals, but we'll get into the hardware of everything, more specifically the PCB that we built and the struggles it took, just making it such a small footprint with all the sensors we wanted to add. After that, we'll talk about, the software of everything, and then just show you the final product. So the sensors that we have on our watch, the pulse oximetry, body temperature, IMU for motion, noise level, and a weather sensor. With this, we're able to get the user's heart rate, their blood oxygen, body temperature, their steps and activity, fall detection on it, and lastly, just normal weather data like air quality and temperature. You can see all of this on the LCD display on the watch itself, but also for more detailed information, you can get it on the app that we have, and also from anywhere in the world, because everything will be database. And if you want to view anything in the past, you can also see that through the database as well.
Yeah, so now that you know about some of our features, as well as some of the things that we want to accomplish, here's our wearable block diagram. You can see our choice in microcontroller, as well as all of our peripherals. Starting off with our choice in microcontroller, we chose the NRF52840 since provided by Nordic Semiconductor. Two main reasons why we chose it. First one was that we needed Bluetooth low energy support, and we're also running this watch on battery support, so we want low power consumption. And luckily for us, it supports all of our peripherals as well. So now moving on to those. Starting off with the weather sensor, it communicates to the microcontroller using IPC, and it measures temperature, like ambient temperature, pressure, humidity, as well as gas resistance. So we get AQI as well. Next up, we have the medical thermometer. This is also connected to the microcontroller using IPC, and it measures temperature of the body through contact with the skin.
We have our IMU, communicates through SPI communication. It collects our thermometer and our data. That data is used for us to kind of go into the data line. Right, and now we have our heart rate and blood oxygen sensor that communicates through IPC. The way it works is that the sensor is pressed against the user's skin and it emits a light. However much light is absorbed by the user's skin will go on to calculate the blood saturation, blood oxygen saturation levels, and the heart rate. Next, we have our volume sensor. It uses ADC. It doesn't exactly work like a typical microphone. It just measures the sound level in the user's surroundings. And if the user is in a very noisy area, it will alert them. Next, we have our LCD display. It communicates through SDR, and it just meant for the user to see their biometrics on the watch. Lastly, we have our UI components. So we also have a rotary encoder, which is just a little knob on the side of the watch, so the user can go to the various screens of the display and have communication with the GPIO. And we also have a haptic motor, which when the user gets notifications, the haptic motor will just feel vibrations go like that. And that's just something like standard.
So in the PCB for our wearable device, we usually go with a 6-layer design for a bunch of reasons. One of the obvious reasons is that using more layers gives us more space to route all the components we're using. And that helped us a lot in getting us down to our final dimensions of 35 by 50 millimeters, which is about 2 inches by 1.4 inches. But beyond that, the specific layer stack up that we use, which is on the left there, came with a lot of other advantages. First of all, PCBs in general have to deal with a lot of electromagnetic interference or EMI, and this EMI can come from the external world, phones or laptops or other devices near your PCB, but it can also come from inside of the PCB itself. And this EMI can be problematic. It can induce noise in the signals on the PCB, which may cause errors or reliability issues. Now we have two ground planes, and because there are these continuous sheets of copper of a conductive material, ground planes are really good at blocking this interference and actually dissipating it. And if you look at our stack up, each of our component or signal layers is right next to a ground plane, so they're all taking advantage of that shielding and minimizing noise that way. And while that does help in reducing noise, there's always going to be noise in any circuit or any PCB. And a lot of PCB designs put a bunch of decoupling capacitors on the surface of the board to try to mitigate this noise. And that does help, but there's a couple drawbacks. One of the biggest ones is they take up a bunch of space on the board, which is a problem if we're trying to keep it nice and small. And also, they only work super well in the area of the board they're placed on. So other parts of the board are going to be a little bit less protected. So an alternative to this, we decided to make something called an embedded capacitor. That once again is stacked up on layers 4 and 5. We have a power plane and a ground plane. And though it's not shown, there's a dielectric material in between those. And that lets those two layers act as a big decoupling capacitor. And that gives that noise mitigation that the individual decoupling capacitors provide without taking up any board space, and it works equally effective on all parts of the board. And then the last advantage of this stackup is that it lets all of our ground planes serve as reference planes. In a PCB, the goal of a reference plane is to provide a direct and low impedance path with the current that flows through all of our signal layers to return to the battery. Once again, you can see that all of our component layers are next to a ground plane, so they all have an associated reference plane. And that, once again, helps reduce noise because, first of all, you're just minimizing the distance that the current is flowing, then there's less chance for noise to be introduced into that signal, but also you're minimizing the area of the current loop. We can minimize the electromagnetic output of the board itself, which can minimize the noise that it induces into other parts of the PCB. So this is how our PCB looked when we were designing it in Altium. You can see in the red and the dark blue are our outer layers where all of our components are placed. And then in that turquoise, that's our inner layer where we route in most of our components. And one nice thing about routing everything in the middle is that it's sandwiched between two ground planes, so it gets the absolute most shielding from the EMI that we talked about earlier. And then this is what our PCB looked like once we got it manufactured. You can see up there on the top, we have our noise sensor and our weather sensor. We kept those up towards the corner to make it really easy to give those access to the outside environment with accurate data. Below that, we have the IMU, which we tried to keep as close to the middle of the board to keep the data clean and centered. On the right there, we have a display connector, which we use to hook up our LCD display with a ribbon connector. A microcontrollers there, and then down at the bottom we have the antenna that we're using to communicate with our app via GLE, and then we have the connector where we're hooking up our battery. And then moving on to the bottom of the board, at the top there we have a body temperature sensor, which is going to press into the user's skin because it's the top of the board, and then below that we have our heart rate and blood oxygen sensor. And as you can see, we soldered that sensor on the board. We did experiment with including it directly on the board as surface mount components, so we figured that if we're doing it this way, we were able to reduce our cost by about 75%. So we thought that this was a solid alternative.
And with all that being said, here's what the final construction looks like. On the left, you'll see our batteries that we use to power it. We use two 3.7 volt batteries connected in series. That gives the PCB 7.4 volts and about 1 watt hour power, a little more than that. On the right, you'll see the display connected to the ribbon cable, and it's currently on. And that little heart there is part of our initialization. You'll see that in the demo. And to enclose all this, here's our enclosure. We wanted to make it as small as possible, so it just barely fits in the PCB. That was kind of the size we wanted to go. And then some of the holes on it. There's the vent hole up at the top, right next to the weather sensor. We have the watch connector bands on the bottom, kind of hiding them on the bottom so they don't stick out any farther than they need to. A charging port for our second revision, where we want to add a charger to it, which we weren't able to do in our first revision of the PCB. Nice rotary encoder hole. And then opening on the bottom, make sure that the body temperature and heart rate sensor were in contact with the user's skin. And then lastly, some mounting holes for the display, so it sits flush right on the top.
All right, I'll take it from here. So moving on to the embedded software side of the project, all of our code is written in C, and we're also leveraging the Zephyr RTOS or real-time operating system. This is essentially an open source library that's supported for a variety of microcontroller frameworks and provides common functionality such as I2C, GPIO settings, SPI, etc. And like I said before, it is an operating system, so there is multi-threading capability, which is also what we use Zephyr for. So going on to the software flow of the project, like I said, it is a multi-threaded application. But before we do branch off into these threads, we first initialize the Bluetooth and all the peripherals, and then we branch off into 4 distinct threads. So the first thread I'm going to talk about is the Bluetooth thread. And the whole point of this thread is to maintain Bluetooth connection and send updated data to the smartphone. Next, we have the I2C thread. This is talking to all the I2C sensors, so that is the body temp sensor, weather sensor, and heart rate sensor. All this is on one bus. It's collecting, pulling data, and storing it within the program. Next, we have the IMU thread. Much like the I2C thread, this is talking to a peripheral. It's only the IMU. This was our only SPI device. So what this thread does is it uses SPI to pull the IMU that performs filtering on these readings. And then with those filtered readings, we perform step tracking and fall detection algorithms. And to expand a little further on the type of filter we used, we essentially simulated a low pass filter in software using this equation right here, which is derived from a KCL equation for a first order RC circuit. And we set the cutoff frequency to be at 5 Hz. And then lastly, we have the UI thread. So this thread is responsible for displaying all our lovely data on the watch, and it's also talking to the rotary encoder for user input. It's also getting data from the I2C and IMU thread. They're basically just variables stored in the program that is accessible and passed into the UI thread. And then to expand a little further on the logic of our UI thread, we essentially have 2 state machines running. So one is the rotary encoder developing state machine. This is interrupt based, and basically the whole point of this is when a clockwise is detected. So we go through these states right here. It will raise a clockwise detected variable that is accessible to the wearable UI state machine. So whatever state you're in, if a clockwise is detected, it will transition into here, and then likewise for counterclockwise. We also have an alerts state right here, where if a certain threshold is met, so say like 10,000 steps or a high heart rate, it will transition into this state, display the alerts page for a specified amount of time, and then it will transition back to the state it was previously in.
So with all that code brings us our user interface. We want to keep it as minimal as possible. So we just have 5 screens that display everything. Starting on the left, you'll see the heart rate, blood oxygen, body temp after that, with a nice just circle to indicate which will change color based on what your temperature is, steps, distance, weather information, and lastly the alert screen, which has a lot more than just fall detected. And now to draw this, to keep it as minimal as possible, we decided to use completely custom display drivers to do this. The first part of this was using buffers to, instead of send individual pixels to be drawn to the display, it'd be best to buffer every pixel that you want to draw, say every pixel on a certain digit, and then send all that at once, and it draws it continuously. After that, we made a custom font. We had 85 different characters from all the numbers, letters, and some special characters that we wanted to show. With that came just very minimal functions to draw them. And then lastly, some of the certain infographics you'll see on the display itself, or a little heart, a circle, triangle on the alert screen. All these were built using custom parametric equations to draw the shapes, such as the heart you'll see there, and it just calculates each pixel needs to draw.
Yeah, so Ben spoke a lot about the UI on the watch itself, and this is our Android application that's kind of a companion app. Starting off with the home screen on the top left, you can see that's kind of like your main dashboard where you can see all your data incoming from your microcontroller in your watch. If you click on weather data, you'll get to the bottom left and you'll see temperature, pressure, humidity, as well as your air quality, and you'll see gauges for all of those. If you click on medical data, you'll see your current heart rate, your temperature, as well as oxygen saturation, and you can also see your pulse waveform. On the right there, you can see the kind of pipeline for our app. As soon as you start it up, it scans the Bluetooth devices next to your watch.
And once it's connected, it receives all this data and then it eventually transfers all this data and uploads it to a database on Firebase. Yeah, so speaking about Firebase, a main goal for this project was to allow users to kind of send this data to their doctors and have a long time database of all of their peripherals, all of this data that they're getting from their watch, in order to kind of figure out trends in terms of sleep as well as like the regular heartbeat. So yeah, we're storing all of this timestamp data on Firebase for the user to like go back to if they need to.
Here's a final look at our product. You'll see it used in the demo video on the next slide.
They're not in there. There it is. It's a play. Yeah. Check the volume. That's fine.
Thank you, guys.
Thank you.
Any questions?
Which of those that you're wearing is operating?
So unfortunately, with our battery life coming in here at 8:30 in the morning, none of them have any charge. And because of the fact that, with our current situation, of not having the charger on the PCB itself, we just weren't able to have them charged and ready right now.
Yeah. It's a little clunky setting everything up.
Do you want to see the one that we have, even though it's off?
Want to hold it? Yeah.
Okay. Any other questions?
So what do you think the biggest challenge in where you got it in this small package, but it's not really quite small in the real product? What do you think would be the biggest challenges in getting the next step towards the real product?
So,
What the backup starts.
yeah. So there were a couple things that we could do to kind of help this. There's a couple of ideas that we have that would help us get to a more final product. One of the big things would be including that heart rate sensor on the bottom of the PCB. That was going to prove too expensive for us to do this time, but doing that would help us save a lot of space. Something else is that because of the way we're powering the board and the power sources, it gets a little warm sometimes. The things pulling more current than necessary, and so putting the power sources on the board would help us reduce operating temperatures and last a little longer, which would help us with that battery life issue. And then, yeah, with the PCB in particular, there's a couple things that we could remove with the revision to and add into that would help us bring it down quite a lot.
If I can add something to that too, it's the fact that having a 6-layer PCB we already were able to make that as, least expensive as possible. But as such an Apple Watch, usually their PCB is about 30 layers, and developing that's millions of dollars. So doing something like that could definitely decrease the footprint of it.
Yeah, and we're like a fraction of Apple's PCB chip. So.
Anything else? Well, thank you guys.
Over there. Yeah, nice. Don't forget to open. Yeah. And then so this one also steps in. Next one, back one. This one also steps back next, and then there's a laser.
Next is the bottom.
You can take this one out. Okay, you can take this one too, because you can next is going down.
Okay.
Oh, actually going right or down.
Is there a laser on this?
No, you don't have.
Oh, this one. You good?
Hi, we are Project Concordia. We are the Smart Home Assistant Capstone group. Let's start by meeting our team.
Hi everyone, I'm Alex. I'm Nick.
I'm Logan.
Here. Yeah. So first, before we get into it, we'll go over the project overview. So the problem is that too many smart home devices are proprietary and not cross-platform, and they're hard to integrate into open source devices that you may have. So the solution is to build an open source smart home ecosystem that allows for easy integration of your peripheral devices and ease of use. So our project includes a central hub, kind of like a Google, like an Alexa or something like that, along with 3 peripheral devices, including a smart camera, smart lock, and smart light. And then we also added a cloud backend for integrating devices and an easy-to-use mobile app for control. So here you see our full block diagram. On this left side here, you'll see our peripheral devices, including the smart light, smart lock, and smart camera down here. The top right is our central hub, including our custom PCB for audio processing, along with audio breakout boards here. And then down in the bottom right, you will see our Firebase cloud and mobile application. And you'll notice that our whole project is sort of glued together with these nano ESP32s that handle all the Wi-Fi and Bluetooth connectivities. So for our software flow, we first start with a user input on the mobile app that then updates a state machine that we host on the cloud, which is then pulled by the central hub, which then does some command routing to control the door and the light, as well as playing an audio cue to allow the user to know that their command is read successfully. We also added some logging functionality to the cloud, as well as some displaying functionality to the mobile app. And then we also added user audio capture to the central hub that is then processed by the cloud and then additionally updates the state machine so we can use voice commands to control our peripherals as well. Finally, we also have a smart camera visual input that goes through a face detection model, which is then the video stream is displayed on the mobile app.
Okay, so I worked on the Concordia connectivity. We use the Nano ESP32 module, and it's capable of using Wi-Fi as well as Bluetooth Low Energy. We use Wi-Fi for Firebase storage as well as our real-time database. And then for Bluetooth Low Energy, we use it for phone pairing as well as the different peripheral communications. And then I'm going to go into why the antenna on the board is essential, and it's really important to maintain that resource throughout the life cycle of our system. So going into that, this is basically the diagram for Bluetooth and Wi-Fi and how we manage it with the antenna. Since it only, that one antenna runs both Wi-Fi and Bluetooth. So on the startup, we see if we have cached Wi-Fi credentials on our central hub, and if we do, we directly connect to Wi-Fi. But if we don't have the credentials on storage, then we can connect to our central hub via our application and customize our Wi-Fi credentials, and then eventually connect to Wi-Fi. And then once we are up and running on Wi-Fi, we connect to our Firebase, and obtain the initial states of the system. And once we obtain those states, we can constantly check if any user inputs are made and constantly check. And if no state changes are made, we're just stuck in this feedback loop. But then once a state change is made, we disconnect from the Wi-Fi and start the Bluetooth service, which is then used to connect to our peripheral devices such as the smart light and smart lock. And then we disconnect from Bluetooth and then reconnect and the cycle continues. And then, so as for the smart light, the way we communicate to it, we use a service UID or a unique identifier, as well as a characteristic unique identifier, and the central hub connects to it. And when we want to turn on or off the light, the central hub tells the light to turn on with the characteristic value. And the way we connect that and turn on and off light is using a relay module, which relays the power from an outlet to turn on and off the smart light. And much like the smart light, we do the same with the door, but instead we use a servo motor to open and close the door.
So for the smart camera, we have a camera that broadcasts the video stream to an IP address on the local Wi-Fi network that the mobile app then maps and embeds into the UI to be viewable by the user. Currently, the camera is using the FOMO face detection model, which stands for faster objects, more objects, and it's a modified version of the MobileNet architecture, which takes all downstream layers after this convolution 5 layer, or 1/8 reduction in space complexity, and cuts those out and replaces them with custom convolution layers with modified loss functions. And so as far as the parts and enclosure go, we have 3 main components inside the smart camera. We have the OpenMV camera board here, and then we have our charge moderator board here, and then our 2500 milliamp hour LiPo battery. And then as far as all of these components fit snugly into a 3D printed enclosure measuring 58 millimeters wide by 100 millimeters long and only 23 millimeters deep. So roughly the same form factor as like the Rainbow propellers. Okay, so moving on to the central hub audio. So here's a simple block diagram of how it works. So we have the microphone, which allows us to capture user commands. And then we have the DAC and the speaker, which can be used to output some kind of response. So our goal with these devices was to basically be able to capture user commands, output some kind of response to the user so they know what occurred, and possibly use it as a music playback device in your home. So here's just a parts list that a list of parts that we use to accomplish these tasks. And so right here we have the speaker, we have the PCB, we have the amplifier, we have the Bluetooth and the Wi-Fi module, and we have the microphone. So the way we capture audio is using a PDM microphone, so pulse density modulation, and we are able to process that with the onboard DFSDM peripheral, which is the digital filter for delta signal modulator. And with that, we're able to convert PDM samples to 16-bit PCM samples, which we then can either save as 16 kilohertz audio or play back as 60 kilohertz. Okay, so then the speaker is driven with the onboard digital to analog converter and a timer. So we have a timer that fires at the sampling rate and moves a PCM sample into the digital to analog converter. So that's how we get the sample. And in order to not be limited by the onboard flash, so we can theoretically have longer clips, we have a onboard SD card, which we communicate with SPI. So we're able to, in real time, using circular buffers, write audio data and playback longer files instead of having to load all that data into memory. And another thing that all these parts allow us to do is do voice recognition. So this is just a simple overview of the pipeline. So first, we start with the user activating voice capture on the app. Then the Bluetooth and Wi-Fi module detects that the user inputted a command and sends that command to the audio board. Then the audio data is captured from the mic and saved onto the onboard storage. We capped it at 4 seconds. Then the data that's stored on the SD card is then sent back to the Bluetooth and Wi-Fi module using UART. And then the Bluetooth and Wi-Fi module sends this data to the cloud. And then once the cloud receives the WAV file with the user recorded voice, we have a cloud function which processes the file and determines what the user said. And then based on if the data contained any useful data, like open the door, then the cloud function will update the fields in the database, and the Bluetooth and Wi-Fi module will then detect that the fields were updated, and then update the mobile devices, so the camera, or not camera, the lock and the light, and then also send a message to the central hub to play a sound that says like open the door or close it or turning the light.
So I'm going to talk about the cloud and the mobile app. So as you can see, our mobile app is pretty good. We have we have the icon, and then we can control the door and the light and the voice activation through the control panel. And we have two cloud functions. We have the logging cloud function and the smart cam, the voice recognition cloud function. So as you know, the voice recognition works by keeping the WAV file in a storage bucket, and then we use that to send it to a Google API, and we get back the parse response. And through that, we can tell if someone wants to open the door or turn on light, etc. And everything is stored in the real-time database. So the whole state of the entire board is like the door and the light is stored in that. So yeah, and then as you can see at the bottom, you can access the SmartCam video feed, and yeah, we're gonna stop there.
This is our custom PCB. It is the central hub to our central hub. It allows us to connect to our ESP32, which we use for Bluetooth and Wi-Fi communication, so that we can receive any information from our peripherals and send them up to the cloud, and vice versa. If the cloud sends something down, we send it out to our peripherals from the central hub, as well as holding onboard storage for the audio so that we can store our WAV files and also send those up to the cloud, and connect to our DAC that then connects to our speaker. And now we're going to look at our final demo video.
So first with the demo video, we're going to show you guys using the app buttons to turn the light on and to lock the door.
Turning the light on. Moving the doors.
Now we're going to show you guys using the voice commands to turn off the light and unlock the door.
Turn the light off.
Turning the light off.
Open the door.
Opening the door.
And now we're going to show you guys the smart camera booting up and being able to view the stream through the app. So here, just press the power button, and then there will be an LED indicator right here, or up here, that will kind of tell you what state the smart camera is in. So right now it's connecting to Wi-Fi. Solid red means it's connected, and then we view the stream. Blue here means that it's streaming, and the green light means that it's detected a face. And that's the
So for possible future goals for this project, if we were to continue working on it or had more time to work with it, we would like to connect the smart lock with the facial recognition that the smart cam has to make essentially a face ID door that you could walk up to, look into, and then enter your home, or vice versa on the way out, lock it on your way out. We would want to add movement detection to the smart camera so that we could ping from the central hub when someone walks up to your door, as if it was a doorbell, similar to how the Ring functions. We would want to add music streaming to the central hub so that you could connect it to Spotify or Apple Music or whatever you choose to stream music with, so that you could play it through your phone. We want to add video logs because we have logging for other peripheral devices, but not for clips of the video. When people would walk past, that you could use it as a security camera as well. And then finally, we would want to implement wake up words. Like you can say, hey, Alexa, to your Alexa, and it'll start listening to you. We would want to do something similar where we would speak to it and then it would start listening to us instead of using the app to prompt it. And that's everything. Thank you so much to Dr. Yoga and our TA Brian, as well as Eric and Alex for all the help this year. Any questions?
With the framework you have set up, and given you're using Google's API for recognizing and discriminating different words and stuff, how hard or easy is it to add, for instance, your wake up word description, these other functions? Is it like terribly difficult, easy to reduce that, or just start adding?
Or a wake up word, preferably we would do it on the device, like processing on device, because sending it to the cloud and receiving data back is considerable time, especially with how varying people's internet connections are. So that would actually be something we would want to do on device. But like stuff like Google searches and knowing what the weather is, obviously we'd want to just work with Google.
Is that pretty easy with that part of it?
Yeah.
Thanks.
Yeah. So, I know this is PCB version 2. What changed between version 1 and version 2?
We had to clean up a bunch of connections as well as add back a piece that ended up being missing in our first revision. We weren't able to get it to like function in order like sending any messages the first time around. So we had to make sure that we added that piece back and clean up a couple of the wires as well as the micro SD card slot because we had a like too many pieces for the micro SD card slot when we could have definitely pared it down. So we made it simpler and fixed a big error on our first version.
Yeah. Quick clarification, guys. What would you say is one of the biggest challenges you guys face?
Probably don't Bluetooth.
Yeah, so probably the Bluetooth and Wi-Fi setup. Mainly the Bluetooth because initially we used the ACO5 module and we configured with that in class in 152. And it doesn't really have one-to-many capabilities. So initially we had two ACO5s talking to two other ACO5s, which is the Smart Light and Smart Lock. And we had to ultimately revert to Bluetooth Low Energy instead because that way we can connect to multiple devices and talk to them.
Thank you.
Then no. Oh, that's like that.
I don't speak Russian.
I'm listening. Hello. Oh, hello. I'm listening. Listen. Just like speak on me. Oh my God. Ready? Hi. Hey,
We're the CE portion of the Gaucho Racing interdisciplinary capstone team. And today we'll be presenting our work on GR24, also known as Gaucho Racing's 2024 vehicle. So for a quick team overview, I'm the team lead, Joshua Thomas.
I'm in the region, I work on the software side.
I'm Camden. I've mainly worked on the software and sensor configuration.
I'm working on harnessing. I'm an ET, I mostly work on the PC.
So our overarching goals as Gaucho Racing was firstly to place within the top 30 colleges at the FSAE Michigan 2024 competition. For a little bit of context, it's a competition held by the Society of Automotive Engineers in Michigan every year. So colleges and automotive industries could sort of connect automotive engineers with automotive companies. Secondly, we'd like to positively impact, part of this challenge would be passing the rigorous technical inspection, which includes high voltage safety tests, a water or rain test, a tilt test, and a locking brake test, and along like 17 pages of more technical inspections. Secondly, we want to positively impact the educations and careers of UCSB students. SAE, FSAE as a whole, the entire point of it is to connect students and aspiring automotive engineers to the automotive industry. And so far, already myself has been like hired by Rivian and a bunch of our teams already into automotive, and we're already creating the connections and the networking that we need to hopefully create a pipeline from UCSB automotive engineers to the automotive industry. Finally, we would like to establish a lasting organizational structure to support iterative vehicle improvement throughout the years. So a quick overview of the whole car's controller architecture. We start with the in-house ACU, or the accumulator control unit, which is in charge of our distributed battery management system. We have 8 segments in this high voltage battery. Each one's controlled by its own BMS, all of which are reporting to the accumulator control unit, which is in charge of its cooling. Following that is the off-the-shelf DTM motor controller. This is the base motor controller a lot of teams use with the motor that we're using, which is the MRAX 228. It's around 145 horsepower, so a little bit more than my Subaru. Next, we have our vehicle dynamics unit. This is primarily in charge of all the vehicle control. But everything except the motor controller is all made in-house. The vehicle dynamics unit which is responsible for primary vehicle control. Then we have the BCM, which is all of the sensory systems and what the scope of this Capstone project is. Downstream of the BCM, we have 4 satellite modules for the front left, front right, rear left, and rear right wheels of the car. Following that, we have the telecommunications module, which is basically used to pipeline all of the data and the signals transmitted on these 2 CAN buses, which is our data primary CAN line for control signal, and data CAN line for sensitive signal for sponsor single store, which is a cloud-based data platform. And then we have 2 auxiliary nodes, which have microcontrollers, which is the steering wheel and the pedals, or pedal box. So a quick overview of our Capstone's goals specifically. Our design motivations for our Capstone project is to monitor the performance of a vehicle during runtime, hopefully make sure that nothing breaks, considering that this entire car is built ground up by UCSB students. There were a lot of points of failure. So we wanted to make sure that we bulletproofed every single corner of this car. Secondly, we want to ensure that the vehicle won't operate over its physical limits. Of course, because everything's built by UCSB students, industry safety redundancy is not like we have to make it. And this is part of the system that we're making. And finally, we want to look for potential improvements. This ties back to our main team's goal of iterative vehicle improvement and design over the years. And we want to lay down the base groundwork system of a sensory system that future cars and future architectures could use. Real quick, I'd like to point out this example control node. This is sort of like this is basically how all of our controller nodes look like. It's encased in a waterproof and weatherproof DTM box with 2 DTM connectors, which are OEM, original equipment manufacturers. And then we have our PCB with all of the hardware logic here, a step-down converter here, and our TNC microcontroller here. We'll get more into that later.
So here's the full block diagram for a body control module, which is the scope of this capstone. It's comprised of 5 microcontrollers, which we chose as TZ 4.1. We zonalize our microcontrollers into 4 satellite modules and a central module. Each satellite module has a brake temperature sensor, a tire temperature, an IMU for tracking accelerometer and gyroscopic data, a wheel speed sensor to track the RPM of each wheel,
Additionally, we have brake pressure sensor, steering position sensor, an IMU for the nose cone, and a linear potentiometer for suspension travel. Each of these sensors, they interface with their satellite microcontroller using their own peripheral interface, such as PHY, I2C. The satellite module then packages the data into CAN, sends it to Central, which sends it to our telecommunications module, which then uploads it to the cloud. So for our first sensor, we have a single pixel IR sensor, which has a dual mode, an ambient temperature mode, and a object temperature mode. We're using the object temperature to track our brake temperature, and we're cross-validating data with ambient temperature, just to make sure we're not getting some outliers values. It is mounted on a suspension AR. Its temperature ranges from -70 degrees Celsius to 380 degrees Celsius. And the reason this sensor is important is because if the brake is overheating, that can impede from doing its function of braking, which poses significant health safety hazard for the driver. So we want to monitor the data from the sensor so we're seeing if the temperature is climbing, we can get the driver out of the vehicle safely. Next, we have a steering position sensor, which is mounted directly on the steering rack right over here. It is a potentiometer, and using that coupled with the IMUs from each one of the wheels gives us the system plate, which is valuable data that we can send to our suspension team, and then we can use it for iterative vehicle development and improvement, which is one of the main goals of our club.
Next, we have the Hall effect sensor. This is mainly used for the tracking of the velocity of each wheel, the RPM of each wheel, and how this works is that the sensor itself has to be mounted 2 millimeters within a magnetic object. So we will mount this sensor on. We will mount the. We'll mount the sensor on top of the wheel and put it downwards with the wheel mount. So when the wheel is spinning, we can detect how many RPMs is provided by each wheel. And this has to be constantly detecting, so we will have to put this on a separate thread on the MCU, so it will not be interfering with other sensors. Next, we have the multi-pixel IR sensor. This is the sensor as the same one as the same magnitude as the single pixel. Is a 32 by 24 pixel sensor, which it will produce a array 668 array, and we can use that to perform like this picture right here. And we will take the highest point of the temperature and compare it to cross-validated with other sensory data to prevent any data that's not, or prevent any data errors, basically, to get rid of any outlier. And this is to make sure that the tires are not overheating, and we can use this data to give it to the suspension team.
Then we have the IMU, which is the BMI23, just as the glove team. We use the X-axis gyroscope and accelerometer to get the data from each wheel, and also there's one IMU mounted on the center of the car to record the data of the entire car. And this sensor is mounted at the nose cone and also on each wheels. And this is mainly used to record the car's gravitational transfer and each wheel's dynamic performance. And combined with another sensors, the suspension travel that I'll go deep into later to get wheel and suspension dynamic data. And through that CAD GIF, you can see that how is the IMU censoring like how each wheel performs. Yeah. And then we have the most important sensor, I think, is the brake pressure sensor. We have two brake pressure sensors because our mechanical team, they decided to break our brake line into two circuits, the front circuit and the back circuit. And by putting those two brake pressure sensors into those two separate circuits, we can say both if the front and rear are working perfectly fine, and to see if there's any leaking. And also through seeing the PSI difference between the front and rear, we can say like the braking balance of our car, because that braking balance is like super important when the car is like driving and turning inside curves. And then we have the suspension travel sensor. This one is just a linear potentiometer. As you can see on that CAD, it's mounted along the shock. It's used to record the suspension actuation. This one actually directly skips the rocker arm assembly and is mounted in parallel with the shocks. And combine the data from the this linear potentiometer with the in-well IMU, which gives us like this detailed suspension performance. So like I can give like an example, like when you see that the IMU is like changing drastically, but the suspension travel is not changing that drastically. That means there must be some connection or problem between the wheel and the suspension shock.
So the first step of the software flow is reading the sensor data. As you can see, we have satellite modules, one for each wheel, as well as one central module. We have to do this because since it is an electric car, there's a lot of electromagnetic interference, and we can't, like ITC or analog voltage, we can only use them for short distances to become very unreliable. To communicate between each of the modules, we use something called CAN, which is an automotive grade communication protocol. It's really resilient to EMI, but even with using that specific protocol, we're still getting about like a 20% error rate. So using ITC is definitely not a good idea. That data will be completely rubbish. But yeah, each satellite module has 3 separate threads. One thread is for writing to the SD card. We do this because we're able to get more detailed data, as well as have a redundancy in case something downstream fails. We have another thread specifically for sampling at a high rate. So just making sure we're getting all the sensors, all the sensor data, and all the events that we need. And finally, the last thread is for sending all the satellite data to central. On the central module, we have a thread reading the CAN line, and whenever we receive any messages, we take that message and throw it into a queue. And then on the main central thread, we then go through that queue. If we have any messages pending there, we're able to process them and do it, like repackage them to send to the downstream. And that's the last step. Sending it to the rest of the control systems, like for instance, the TCM, which is handled by the data team, they take that data and they send it over to SignalStore, which is the cloud service. So then we're able to monitor our car's performance through the cloud.
Lastly, we have harnessing. So harnessing is split into 3 parts. We have the primary harnessing, which is in charge of the central and the TNC communication. And we also have the front satellite harnessing and the rear satellite harnessing. So the steps we do to do these harnessing is that we measure and decide the routing path through CAN. Then we put them in this software, and this is an example of like the main harnessing example. Then we measure it directly with these measurements, and we put them like we test it onto the chassis of the car to see if it fits. We then cut over like 10% of the measurement we did, so to prevent any manufacturing error. Then after we cut all those wires, we put them in like the TextFlex protective sleeve to prevent any environmental damage throughout the competition. Then since there's a rain test during the competition, we have to cover all the sensors within epoxy and within the spark glue so it does not get destroyed by the water test. This is like an example of the wires being cut and laid out throughout the
Real quickly, this demo video was recorded a couple of days ago. As of 9 a.m. today, the first electric vehicle created by UCSB students, ground up, is currently driving around the lagoon.
How do you play this thing?
Here is our GR24 car. At the time of recording, the car isn't finished, so each of these mounts are temporary. Later on, we'll use brackets and some glue to make a more permanent mount. So here are the brake pressure sensors. They are connected to the central MCU located at the front of the car. Here are the 2 front satellite mounts. If you see the blue 3D printed piece, when we mount this permanently, we'll have another piece that we can glue on. That'll make sure that that box doesn't fall off. You see there's a PCB inside each of these boxes with connectors on the outside, and these wires will go head to one wheel. Right now they're in the open, but we'll sheet them when we're able to mount everything permanently. Here is the IMU that's responsible for the wheel's orientation, just to make sure that our wheel's in the wrong angle. Here is the brake temperature sensor, and it'll be mounted in the same general area, but pointing towards the brake. And here's the wheel speed sensor, looking at that gear and able to get the rotation from that. On the software side of things, here's an example output from one of the satellite modules. If you look on the left-hand side, you'll see that we're displaying tire temp, brake temp, suspension, and last RPM. If you look at the graph, you can see that all these values are actually getting updated real time. So if we move the suspension travel, that'll get updated. If we point the temperature sensor at something at like a little bit hotter or a little bit colder than before, then that'll get updated. And last RPM also will get updated as the wheel spins. This information is right not only on one satellite, but do keep in mind that this is replicated across all 4 of the wheels. So the central will receive 4 times the amount of information. We're only displaying one of the satellite nodes just to make it a little bit easier. And here we have just the raw data. Each of these cells get updated with the newest time factor. So we can see that they're getting updated fairly quickly.
Yeah, thank you. That's our presentation. Special thanks to Professor Yoga, Brian, Alex, and Eric for helping us walk through this presentation and make sure like nothing goes chaotically wrong. And thanks to our biggest sponsor, Single Store, for giving us the funding to actually create this crazy car. Any questions?
Yeah, I got one. Were you tasked with using the very powerful main battery stack?
No. So GLV so GLV and general low voltage and HV need to be completely isolated. One of the technical inspection checks is they actually just check continuity between both lines, make sure they're not grounded in the same place, that make sure they're not derived from the same place. They're 2 completely separate lines. In order to start the power the car on, it needs to pass a bunch of fuses basically using GLV to then create close the latches to start the actual high voltage battery. That's how most electric cars work because they shoes you can't really just fire the battery up. You have to first recharge it. Yeah. Yeah, you had a question?
Yeah, I'm wondering about the 20% error rate on CAN bus. Is that now didn't we know what CAN bus is? I know use it. Is that in most vehicles is that a error rate that you live with, or is that something that's
For our vehicle specifically, it's an error rate we could more than well enough live with. We have a lot of a parity stuff in our data itself just to cross-reference everything to make sure nothing really freaks out. I think in most vehicles, because they're actually using proper shielding and channeling or cabling, I think the worst error rate I've seen is in an Axis CAN bus, which was 32 feet long, routed spinning around the vehicle, and it was about 15%, and that's commercial. So 20% for hobby, I think was not bad.
That's raw data rate. There's error correction.
Oh, we have error correct. Yeah, I think for most CAN lines and systems, you have error correction, but usually because CAN, the way it works is that it's twisted pair of the exact same opposite signal. Any noise that's incurred cancels out when you subtract both of the signals together. So even though we are getting such high noise, we're still canceling it out from the natural nature of CAN itself, which is sort of why we're able to live with the 20% error rate, is because that's technically the error rate, but we're subtracting all of that out. And if you are curious as to where it happens, in the back of the car where the HV components are, that's where most of our data is getting messed up. Yeah. It's nowhere near close. So the Hall effect sensor itself is just it just shows the binary signal. Its refresh rate is sort of the max RPM we could go to. Do you remember the refresh rate itself? It's just
the refresh rate is just how fast we can pull the sensor. So
it's much faster than we needed to.
We can read up to more than 1 million RPS. So we're definitely not reaching that on that.
Yeah. Or if we were, we'd have a big issue. Yeah.
That would be a very good.
Oh yeah. Any other questions?
Oh, sorry.
side of one over here, one over there. Then there's also pointers. This one has laser. That one doesn't. Oh, it does. JK. You can also use switching over here.
Good afternoon, everyone. We're Team Impro, and we've developed an electric wheel that quickly turns your bike into an e-bike in seconds. I think we're all familiar with the classic problem of riding a bicycle. Sometimes it can be really tough to go up hills, range can be a little bit beyond us. And so millions of people like ourselves buy an e-bike, but this year we found that e-bikes are not a great fit for everyone, and for good reasons. A good quality e-bike is expensive. It goes for about $2,000 and it's beyond an average person's budget. And unfortunately, they're prone to theft with 250,000 e-bikes stolen on a yearly basis, making people choose not to invest in it. And we're students. Most of us do not have elevators and space in the apartments. So imagine storing a 65-pound e-bike in a small apartment or carrying it up a flight of stairs. Many people reserve to conversion kits, and as the name suggests, it converts your bike into an e-bike. But the biggest drawback is they're hard to install. They come with a lot of small pieces you can see right here, and they require special tools and expertise that most people don't have. That makes the installation anywhere from hours to days long, and they're unsafe. The batteries are poorly manufactured, making them more likely to flame up, and when they break, there's really nowhere to service them in the US. You have to send it to China, wait a couple months, and there's no guarantee that it works. So we looked at this market and we found that there's a really big gap in the market where people want a modular solution that utilizes the existing bike. And so we've developed an electric wheel that turns your bike into an e-bike, really any mechanical bike into an e-bike there's a burden from, within seconds. The system is comprised of 5 subsystems. There is the mechanical, the throttle assembly, the electronics, and the controls and powertrain electronics, and a mobile application. Starting with the mechanical system, as you can see in here in the CAD, there is a motor that drives the wheel through a sprocket and chain system. And when taking a deeper look inside, you'll see that there's 3 components, the motor, the battery, and the electronic sled, all of which are compactly sitting near the axle to try and minimize the weight distribution, and that ultimately makes handling very easy.
So next we have the throttle assembly. So the main purposes of the throttle assembly are to allow the user to control the speed of the wheel and to activate the wheel. The throttle assembly consists of 4 pieces of hardware, a microcontroller, NFC reader, a OLED display, and a throttle lever. On the right, there is a CAD design of the throttle housing. It houses its purpose is to house the microcontroller, the NFC reader, and the OLED display when it's mounted onto a bike. And in addition, it features a built-in clamp that allows for easy installation of the throttle onto a bike without any tools. So here are 2 images of throttle housing that has been mounted onto a bike. So next we have the OLED display. So the OLED display provides users with the ability to The OLED display provides users with the ability to quickly check important information such as the wheel's battery life or speed directly from the throttle. And here's a demo of the OLED display. The demo shows how the throttle updates how the OLED display updates whenever the throttle receives new battery percentage or speed values from the wheel.
Of course, theft is a big concern when it comes to any e-bike, and ours is no exception. And to make sure that not just anybody can like hop on and ride off, our wheel is locked by default and completely disabled. To unlock it, we have an encrypted NFC key fob that we tap to this NFC reader that is embedded in the throttle. The NFC reader then authenticates the key fob, and if everything checks out, unlocks the wheel.
The wheel itself is powered by an EC4 motor that nicely fits our product's target power and its size. Although the motor itself is factored 2,450 watts, we're operating it at quite a lower power level, which is also set in the product settings. This motor is connected to an off-the-shelf motor controller, which, in addition to providing data back to the throttle about the wheel's speed and the power being consumed, is also highly configurable and able to be tuned with great ease to maximize the power efficiency of the entire power. In order to keep all of this safe during charging and while you're riding the bike, the battery is directly connected to a battery management system, which is responsible for, in addition to keeping everything safe, also reporting back to the throttle the current state of charge of the battery and any faults that might arise. The battery pack itself is composed of 39 cylinder cells, which are arranged in a 13 series 3 parallel setup, which as an architecture provides 9 amp hours of battery capacity at a nominal voltage of 48 volts. This is sufficient to power the bike for approximately 25 miles at a maximum speed of 20 miles an hour. Here you can see a view of the prototype that we built. Commonly visible is the motor at the top, the ESC in the middle, and the battery in horseshoe shape around the outside. Under the green plastic housing is the battery management system itself. This was quite difficult to build, and it comprised a great majority of the technical complexity in our build, which required several months of pleasure engineering to get the spot welding, the wire routing, and to properly respect all these fault tolerances. Because as you can imagine, I kind of see here, it's really tight on the inside, and get all the moving parts to slide across each other without stacking to each other was quite difficult.
Yeah, so the center of our control system is the wirelessly equipped Raspberry Pi microcontroller. Once powered on, the throttle automatically establishes the preset Bluetooth connection with the wheel. As the user depresses the throttle lever, the throttle then sends the desired speed command back to the wheel. The wheel filters these inputs, performs certain banding checks, and then updates the duty cycle of the ESC. It also collects certain script info from the ESC and DNS, such as speed and battery usage, which are reported back to the throttle and mobile application. We also offer location tracking through an onboard GPS receiver. Location history is recorded locally and can then be operated to the mobile application once you connect it. Additionally, to enhance security, the user may opt in to real-time location tracking via a cellular modem, which reports back the location in real time and can be monitored remotely.
E-bikes are stolen very often, and so to provide this peace of mind for the users, we integrated a mobile application, and it tracks basic things like speed, the total distance traveled, the duration, but also in the unlikely event that it's stolen, we want people to be able to retrieve it, and that's why we're offering also geolocation tracking services that maps the location of the wheel at all times. So on the right, you can see the map with the blue circle representing the wheel. And on the left, the basic parameters like average speed, distance, duration, and any health parameters that we could incorporate. Here's a quick demo of our wheel. One of our value propositions is that we want to make the installation very quickly. And we're estimating that it can take about 60 seconds because we're utilizing the existing quick release that a lot of bikes have. We performed some initial testing where we had someone ride on the bike, one of our teammates, which easily was able to carry them. We tried to test the handling, and actually it was perfect. There was very little difference between that and any regular bike. In the lab, we performed some initial testing on the battery and the integration of the systems. As you can see inside, none of the components are moving. They're absolutely stationary, and it's only the housing that spins that then rotates the remaining wheels. Here's the phone app. You can see kind of the location it's been at, and then in tracking the wheel, you'll have the blue dot moving along the location of the wheel. We all know what that is. We'd like to thank our Professor Yoga, and CMSI for sponsoring us this year. We'll be happy to take any questions.
You have a plan, or would you have plans to, you waterproof the fence?
Can you repeat that question?
Can you waterproof the fence?
Yes, that has to be part of the plan, since roads are sometimes wet, no one cancels weather. So one of the ways to combat that is have a waterproof casing. We did not demonstrate it in here just so that you can see the components inside, but yes, it would be ideal to have everything waterproof.
The throttle is independent from pedaling, right? Is there, can I pedal and throttle at the same time, or what is the?
So the throttle is wirelessly connected, to again, make the installation very easy for an average user. So really the plan is that you can pedal without having to use the throttle, because again, the battery can die after 25 miles of commuting. And in the event that you do want to use the electric assist, you can power that on very quickly. Yes.
So how did the versions, the front wheel make it like that much harder to pedal just normally?
So to some extent, but all the weight is concentrated very closely to the axle, and that minimizes any issues with that. Part of the design is that it's not intended for mountain biking, for example, where you would go down a hill, take really steep corners. It's meant for general commute on relatively flat surfaces, somewhat hills, but again, not mountain biking. In our testing, we did ride it, and it felt, at least for low speeds, it felt perfectly normal and really fun too. Any more questions? Sweet, thank you.
The unwanted team. So, this one has laser, this one doesn't, but both of them. This clicks forward. These two both of them clicks. Okay. Okay.
Hi, everyone. Thank you for coming to the unmanned special team, and I'm excited to share what we've been working on this year with them. I'm Cameron Garrett.
I'm Winjin Lee.
I'm Dhruva Garval.
And unfortunately, Darren is not solo with us today, so we're going to be doing our best to present them. So first, I want to talk about our mission and goals we have for the project. Then I'll talk about some of the key technologies we use to accomplish those goals. And finally, we'll show you a demo showcasing some of the success we have this year. So our mission is to design an easily deployable unmanned surface vessel which can map and survey coastlines using a marine radar without reliance on cellular network connectivity. Some of the applications of this technology are mapping coastline erosion, maritime navigation, and potentially military reconnaissance. A secondary goal was to evaluate the capability of a marine radar for performing SLAM. This is an interesting application for a marine radar because of its longer range, increased durability, and increased resilience to adverse weather conditions such as fog and rain. And finally, we wanted to evaluate if we could stream remote telemetry such as live video from the map we generate back to the control station without a cellular network.
So here's our hardware block diagram. We have 6 key peripherals on the both sides. Camera and GPS are connected via USB port. ESC and IMU are connected via GPIO pin, and also the ESC used PWM while the IMU used I2C. Finally, we have the radar and radio are connected via Ethernet port. In the middle, the pi we see input from all the sensors and output to the thruster, which output the PWM signal to the ESC, and the radio communicate two-way with the pi. And on the right side, we have the control station. We have another radio that connects to the laptop via Ethernet port. And this is our single board computer. We chose Raspberry Pi 4B. It runs Ubuntu. We use it to control hardware, process data, and write RAS2 package. We will cover how we control our RAS2 framework in the further slides. It also runs the DSCP, Dynamic Host Configuration Protocol. That's because communicating with the radar requires middleware software. So we configure the Pi to assign a static IP for the radar.
For our radar, we selected a solid state radar with a 24 nautical miles max range. This radar divides 360 degrees into 250 spokes and collects 100 to 200 intensity values depending on the range. Each of those intensity values maps to a pixel, and each pixel ends up being a roughly 4 meter resolution on the ground. For communicating with the UFB, we selected the Labs mini shutter radio. This radio operates in a 2.4 gigahertz band and has a theoretical maximum of 10 kilometers and a max throughput of 100 megabits per second. Unfortunately, in our real world testing in urban environments, we discovered a max range of over 2 kilometers until it disconnected when we broke line of sight.
So as Cameron mentioned earlier, one of the important things to us was streaming back video data to the control station. Because we are manually controlling the USB, we need to know where it is. If it does get far away, we need to know where to steer and things like that. So that's really what the camera is providing. So we just used a simple USB camera with a pretty wide angle lens and IP67 certified water resistance just in case. For our ground truth positioning, we're using a Neo M8 GPS, which has about a 2 to 2.5 meter resolution and also connects via USB. The main challenge with this GPS is that it requires direct line of sight access to the sky at all times, but our radar stand is mounted directly above our control electronics box for balancing. So to circumvent this issue, we use an antenna which we could then attach to the top of the radar and prevent that from happening. To estimate orientation, we used a 9-degree of freedom IMU, which has 3 axes of rotation, 3 axes of linear acceleration, and communicates via the GPIO pins to use I2C.
All the USB we selected 2 T200 robotics thrusters. Each of these can draw up to 200 watts, so we have them configured. And together they can propel the USB at over 10 miles an hour. The power, the onboard electronics, and the thrusters provide a challenge. When the thrusters change direction, they draw down current and draw down the voltage on the battery. So this causes voltage dips and will mess with the onboard electronics. To mitigate that, we implemented 2 distinct power supply solutions. So we have 22 amp hours of LiPo batteries allocated to the propulsion system, and a distinct 6.5 amp hours allocated to the onboard electronics. As the basis of our USB, we selected a 7.5 foot inflatable pontoon boat that weighs 50 pounds at a low center of gravity. And on top of it, we constructed a 4-foot radar tower, which elevates the radar and mitigates multi-path interference from the water. Additionally, we mounted each thruster to the bottom of each pontoon, which allowed for zero radius turning. Finally, we began assembly of our electronics enclosure, which uses waterproof connectors and jaded voltage plastics to allow radar and radio IO to exit safely. We mounted the batteries and buck converters to bring the voltages within 12 and 5 volts for the rails and attach the rest of the electronics inside. And the final product uses 3D printed shelving to organize it and extruded aluminum to attach the antennas in the recommended orientations.
Once we had the control electronics ready to go, we wanted to test that the thrusters and the radios work properly. So we actually took the USV without the radar stand just to the Creo pool, actually, tested out that we could use an Xbox controller to input direction commands and basically just steer around the pool at will. This is just a couple pictures that we have of the USV fully assembled. On the left side, you can see before we actually went in the water, and on the right side, that's how we circumvented the GPS's line of sight issue. One more quick shot of the USV fully assembled, and then we get to our control station GUI, which is pretty much the only way that the user interacts with the USV at all. So this was just something that we wrote using a Python web GUI, and it's divided into 4 sections. In the top right, you can see a diagnostic panel. So I'll talk about the ROS framework in a second, but all of our sensors are sending heartbeat messages every like 2 or 3 seconds to let the USV and the control station know if the camera's still on, if the GPS has a fix, if the radar is scanning, and of course, if the Raspberry Pi is even connected at all. In the top left, we have our video stream so that we can make sure we're steering properly. And in the bottom half, we have our radar images. So to get those radar images was quite the challenge. This radar is entirely closed source. So we spent, or I guess Max spent the better part of the school year really reverse engineering the radar, understanding the network protocol, and being able to communicate with it at all. So on the left side, once we understood how to communicate with it and send it control signals, we were able to take the stacked polar image and just stack up on the left side and create that. We used OpenCV to wrap these around in a full circle to create a Cartesian image on the right side. And knowing that the radar worked, we wanted something better than the Capstone lab to have a more ideal frame of reference. So we actually used the Goleta Beach Pier, where we can see easily identifiable landmarks, such as the coastline, the pier itself, and then surrounding buildings. We were able to overlay these on top of each other, where we could see pretty accurately that we were mapping the correct features. And we used the radar scan to use the pixel lengths compared to Google Maps to determine that we are scanning each pixel is about a 5-meter resolution in the real world. Using these radar images, we wanted to filter them a little bit to provide better coastal mapping. It's a little blurry on the slides, but on the left side, we use morphological and bilateral filtering to first remove noise and then blend intensity values. On the right side, we use thresholding and contouring to basically just do edge detection and create outlines of the shapes that we were seeing. So we've mentioned ROS a couple times, and we'll kind of go into how this middleware framework works. But essentially, we have our radios on the side of the USB as well as the control station, which are sending UDP messages between the two. Once they're received at the USB, we have this node called the radio. So ROS has 2 main components. It has nodes, it has topics, which we like to think about like a mailbox or a mail system in general. So a node will be the mailman or the home recipient, whatever, with the topic, that box in the bottom left, that video stream, being the mailbox. So when someone puts mail in that mailbox, we call it publishing, and retrieving mail is called subscribing. So we first publish from the video to the video stream, which the radio can receive those images and send back to the control station to create a video stream. We then publish to the thruster control to send GPIO messages via PWM. The radar has a send and receive. So we're sending radar control messages, whether those are turning the scanning on and off or adjusting zoom level, and then the radar in turn sends back polar images for later processing. We have the IMU and GPS, which are providing sensor data for something that we do called localization. Now, localization basically is just the idea of knowing where the USV is relative to its surrounding environment. So initially, we tried to do something called dead reckoning with the IMU, but we ran into an issue with using a cheaper IMU, and we were just getting a lot of drift. And we tried using this algorithm we found called CFIR, which uses exclusively radar data to stitch together a map. But we ran into another bottleneck, which is the Raspberry Pi's computing power. Simultaneously getting all of the data and processing it to create a map was just too much. So we did something called bagging, which ROS allows us to subscribe to any given topic, save it to a file for later, and then play it back for processing in the lab. So eventually we did get a bag that we were able to work with. And this shows kind of what the output of that was. The purple, and I guess the colored lines in general around the circle. Here we go. Replay this somehow. The color dots in the circle show the point cloud that we generated with the red triangles in the middle showing the last 3 estimated position and orientation values of the USV with relation to the lagoon. So I've been talking for quite a bit. I'm going to stop talking now and show you a little video of what the USV's progress looks like so far. Maybe not. Maybe I won't. So yeah, we'll do it again. Okay, we just wanted to end off with some quick acknowledgements to Professor Sukapalli, as well as our TA Eric, and then our three sponsors and mentors from AV, this being Phil, Matthew, and Ryan. We wouldn't have been able to do it without all of you guys, so thank you very much. And if you guys have any questions, now's the time.
So, it sounds like you intended to process so much stuff that turned out to be too much for the Raspberry Pi. So you said you bagged the data and analyzed it later. Was the original intent was to do that analysis in real time?
Yes. Initially, yes. But by the time we had gotten radar data and all those things, we just didn't have the time to switch to a new SBC and get all of that working all at once.
Did you get as far, did you look at any SBCs that might be able to accomplish that?
Not right now, because we kind of just decided we're not going to be able to. Let's just process it later on. Yeah, definitely something for the future.
Your bill of materials is pretty sturdy. Do you have any, like, once you assemble the machine, do you have any issues operating it? Do you have to make any repairs or?
A couple thruster issues here and there. Definitely testing in the lagoon. The primary issue was just running into whether there was a rope or a netting and things getting caught in the thrusters. That happened a couple times. I think we actually broke one thruster at one point. Our last test resulted in them being pretty much dead.
Stuck on the lagoon once, and we had to leave it overnight, and then come back with a giant metal hook and
Yeah.
fish it back.
Yeah, it's
squeeze
pretty
it out there.
But in terms of structural stability, it was totally fine. It was pretty much just running into things in the lagoon that we couldn't account for before.
Okay.
So I know the radar you guys are using is usually mounted at like the top of a very large sail. And you guys have it mounted with another obviously up and down from that. So I'm curious if that presented any challenges as far as the readings that you come in, and just maybe talk a little bit about that.
I'm sure that it didn't help cutting it down so low because it's supposed to be up like 16 feet on top of the motorboat, and the closer you have to the ground, the more the stuff around you acts like a giant reflector, just cooling that. Has more options for signals to bounce off hitting the radar.
Have a slide.
But we didn't get a chance to do like an A/B comparison of what it would look like if we did have it up high. I think if we had moved it up, it wouldn't have helped a ton just because the range scale of this radar is so massive. Like it's really, we're looking at things that are, I don't know what the scale of this is, but this pier is I think 500 meters long. Yeah, so.
And that horizontal line that's kind of perpendicular to the pier isn't actually a physical feature, but when we were testing, we're pretty sure that was a wave that was a little bit higher. So we definitely did pick up some noise here and there, but we're limited as far as how big we could make the USV in general. Down. Chilling. All right. Could have been worse.
Yeah, that was
Could have
fun.
been a lot worse.
All right, guys, we are kind of done. We're done a bit early. CJ is supposed to be here at 12:30, so just please wait. I'll give it some time to someone to ask. Now, can I put the video on?
Yeah. Fun.
Or the fishing line, or the one who eventually skipped the boat. Or the videos of us streaming out.
Right. Bro, you guys have the unlucky team.
We had two people saying get things caught in the lagoon. We almost tipped it over like 3 times. We did the fishing. Did I show you that helicopter man? Yeah, we think we don't want to fishing.